Here we go with the second part of the course today, which, as I said, will be pretty long and will extend on to next week, the fourth week of the course. It's long because it contains a number of things that are in some sense relatively different, as you will see. They'll come, if you go and look perhaps on the Hennessy Patterson on some books, you may find many of the things that we'll discuss in very different parts, different chapters far away from each other in the book. I decided to put them together and to keep them together because I think they belong somehow together. It's always the same single idea, which has proven to be one of the most useful, proficient, helpful ideas to increase performance of digital systems, and is the idea of predicting, of trying to figure out what will be the outcome that I don't know yet of something and advancing as if that were the case. And we'll see. Of course, it's not as easy as it looks because maybe we make mistakes and we have to honor our mistakes and do something about that. But it's a very, very powerful idea used in very many different areas and has many incarnations even inside your processor. So we'll look at that for a little time, and there will be an allusion even at the end of this course, of this lecture, to the fact that we'll come back to the idea of prediction and speculation, even when we will be looking at statically scheduling processors. So at the next chapter in this course. So the theme for the rest of today and for next week is going to be what I just mentioned, the idea that if there is something that you are waiting on and you cannot proceed, naturally cannot proceed further, which happens a lot of time for very many different reasons, one option is to say, okay, let's make a guess and let's proceed tentatively with the understanding that what I may be doing, what I will be doing, may be wrong. So there are two general problems that are going to take essentially all our time today and next week, which are, on one side, how do I make a good guess on something that is not known yet in the execution? What is that my best guess so that I can advance and hope not to have to undo things? And the second is, well, what happens if I was wrong? Because clearly I will be wrong sometime, right? And sometimes, in some cases, maybe I have things that to undo the work is just zero cost. I will just ignore what I've done and continue. But in very many cases, I may have some work to do to compensate, to put back values that I have overwritten by mistake or things like this, to sort of explicitly go back to the situation before my wrong execution of some instructions or my wrong speculation. The difference between these last two is, of course, very important. If it costs nothing, you can always do a guess and you don't care how good is the guess, you are always going to gain something. Maybe it costs a lot of hardware, but in terms of time, it's always a gain. More commonly, it will cost something to undo what you have done abusively without being authorized because you made a mistake, and then it's a sort of is a game how good my guess can be, and is that going to be on average sufficiently good so that my mistakes are not undoing the advantage of the idea. The difference between costing something and not costing anything is also depends on the implementation, right? I can, for the same kind of situation or type of speculation, sometimes is how costly is my implementation. Maybe some more costly implementation achieves the zero cost, and maybe a cheaper implementation actually makes me go back and actively do something for a number of cycles to compensate. And so these are the two problems that we are going to study in very different contexts, in some different contexts at least, for the rest of today and next week. So the first question is, have we already seen any of this that we have done really in this course? And there may be things that you have seen in other courses before, and I'm not alluding to this. I'm alluding to really stuff that in the previous videos you have seen. And I want to make a break here. I'm never sure whether you like or hate my little pauses in the videos, but I really want to do one because, okay, of course, everybody understands that if I'm asking this, the answer is yes. But of course, the real question is, where have we seen it? And I really think that you should be able to say where we have done this. Modulo may be spending 15 seconds to think where we may have seen it. So, little break. I hope you have a guess, and the answer is yes. When we were doing precise exceptions, we did not describe it at all as a form of prediction and speculation, but in fact, it was. We have made a very simple prediction, the simplest possible, which is usually there is no exception. So let's bet that this instruction has no exception. And we have speculated that we can execute that instruction and the instructions that follow, right? If there is a load that has a TLB miss and therefore needs to invoke the operating system to fix the TLB miss, the instructions that follow cannot be executed. And we completely disregarded this, and we said, okay, no, but I continue to execute, and I'll try to fix things later by implementing this notion of precise exceptions that, again, we didn't describe it this way, but essentially are simply a form of speculative execution. So let's go back to it. It's the same slides that we have seen before, but let's try to reinterpret them in this spirit, right? We have executed, or we have executed a number of instructions, including instructions that are after a load. So we have we have predicted that this instruction, like anyone else, will not have an exception, and we have speculatively executed these instructions after. You see that there is one here, this one here, that has been executed completely, right? Because I have already the value, so this, whatever this instruction is, and I have no idea, but this has been executed and completed already, but has not been committed yet. So what we have done in this speculative execution scheme is that we have taken one bit here in the reorder buffer, and we have used this to say, I mispredicted. In the specific case, the misprediction is, oh, there was an exception, because I assume that normally there is not in all cases, but here there was one, right? So we can read again this column as there was a misprediction as opposed to there was an exception, because they are the same thing. And what we do is that we just recorded the moment we see this misprediction, in the sense the moment we discover that this memory instruction has a TLB miss, what we have done is that we have simply recorded the fact that we mispredicted. And then we have continued as if nothing happened, and we took instructions that precede this misprediction in the original program order, and we have been kept doing what we do, that is, for instance, committing them, sending to F3 to the register F3 the value that we had. This until the moment the misprediction arrives to the head, to the moment that we need to announce to the world that we have done this instruction. And that was the moment where we decided to not commit. In fact, in the specific case, because of the exception, we don't even have a value, so there is no way that we can commit this. But this is the moment that we take the action, the correct action that we should have taken for this instruction, but which we incorrectly predicted and we didn't do. So we predicted there is no exception. We didn't do anything about this instruction so far because we thought there was no exception. But now that we know that we mispredicted and there is an exception, this is the moment where we are going to act on this exception. And we are going to raise the exception. Just before doing this, what we are going to do is to clear from the reorder buffer everything that follows. So all the instructions that have been executed or started or placed in the reservation station with the intent of eventually execute them speculatively, we clear, we throw away because we have been executing them abusively somehow, right? Without any authorization to do so. So this is the situation. And again, I re-describe the same thing that we have seen last time, but trying to use the words and try to emphasize this as a form of speculation because it is. And it is a very general idea, right? I keep everything that is after a prediction into a buffer, so I don't show it architecturally to the user. I don't write into registers. I don't write into the memory until I know what is the outcome of the prediction. If a prediction turns out to be correct, I continue and I will announce these results to the world, which is this commit that I do. If I realize at a specific point that I made a mistake, I just throw away whatever follows this prediction, follows in program order, but follows also in timing this prediction, and I throw it away. And the reorder buffer is there. We have put it there essentially for doing this job. Maybe we didn't describe it this way, but that's exactly what it does. And the beauty of it that we are going to exploit very soon is that once it is there, because, for instance, we said we cannot live without precise exceptions, but once we have this method, we can use it to predict whatever, to speculate on whatever we can predict. And that's, again, what we are going to do in a few cases today. Okay, so this is a list that I'm going to pull out and fill new items as we go today and next week, with a list of things that we can predict and speculate upon. The first one are exceptions, maybe not precise exception, but exceptions, right? We predict exceptions, we predict the absence of exceptions, and we speculate accordingly. So what can we do next? And next comes probably one of the examples that maybe some of you have already seen, at least partially in other courses, which is branches. It's another place where we tend to have to wait because we need time to figure out from the data, from some data maybe that I need to compare, to do some comparison, and from that comparison decide whether I should execute this or that, an if or the else part of a branch. And where I need actually very early to make a decision, I would want to make a decision very early, because the moment I fetched the branch, the next cycle, or even in the same cycle, if I am in a superscalar processor, I would like to fetch new instructions that corresponds to the actually correct thread of execution or sequence of executions, right? So it's a perfect example of things that we don't want to wait to resolve, and we want to go ahead as quickly as possible. And we can do predictions. So of course, the prediction here is not going to be that easy, right? It's not like when I had the exception and I said, oh, I don't have exceptions, because 99.9% of the time there is no exception. Here is much more difficult to know what happens. And there are two techniques that we will think about, where we try to learn from the past what is happening in our program in this execution, and dynamically on the fly at runtime make a prediction, or try to have some preconceived notion of what to do, and maybe inform our compiler of these preconceived notions, so that it can do sort of suit us best. And speculation maybe is the part that we are going to start with, because in a simple pipeline, maybe we did already something that essentially is a minimalist form of speculation, and we can do much more, and we are going to use exactly what we have seen a minute ago through the reorder buffer. We are going to adapt it to this. So let's start first from the speculation, and then we'll come back to say, okay, how do I make a guess? But given a guess, what shall I do? So I'm going now to show a few slides that I didn't show in the little reminder in the first week, but actually I alluded to then, and I said, go and see them by yourself. I'm going to show them now because they are sort of useful here. If you remember, we had observed together, we have discussed together the situation of data hazards in that reminder. That is one of the biggest problems that we have in a simple pipeline. The fact that we have a causality problem, in the sense that we need to use at some point some data that are not yet in the register file. And so we need to do something like stalling the pipeline and so on and so forth, that you know very well. And at that point, I told you, of course, there is the same problem. It's qualitatively the same problem also for control dependencies, that is for branches that create control hazards, where there is exactly the same causality problem. And here it is. So take this little program that has a branch here that depends on the equality of these two registers, and if they are equal, we jump to loops. That is, we are not going to execute this instruction that just follows. And the problem that we have is that we will not know if these two registers are equal before the end of the execution cycle, because it's our ALU that is doing this comparison. At the same time, it's clear that I need to fetch the next instruction here. And so what I would like to do is to fetch the right instruction here, but I'm 2 cycles before I will ever know if that is the right instruction or not. So it is a causality violation. It is a problem that if we don't want to speculate, we need to do something to solve. And it is clearly also a place where we like already the idea of predicting and speculating, because we need information before it can ever be available, right? It's one of those bad, tough situations. One of the things that probably you have seen in your bachelor course is that, for instance, you can, at least the simplest thing that you can do is to say, okay, but during this this decode cycle, I realize that this is a branch. So what I can do is to say, okay, forget it. I will not let the fetch complete. I will let do again and not complete. When I will have the information, I will let the fetch go again with the right value, right? So it's essentially the same kind of bubble kind of insertion um, that that we have done for the data dependencies. But basically, we let the fetch and decode unit do their job, but actually we keep annihilating this. And how do we nullify it? For instance, by replacing the result of the fetch on the fly with an OP, or basically putting an invalidate on the fetch. Now, you probably know that people tend to do something a little bit smarter than this, which is, in a sense, a form of speculative execution. It's not a speculative execution, in fact, is a speculative fetch and decode, and probably no book calls this speculative, or uses the word speculative for this case, because it's particularly trivial, but in fact is a form of speculative execution, of speculative operation of our processor. And the idea is what we see in the slide, right? I let the next and the instruction following continue to fetch and decode. The beauty is that they don't affect the state, the architectural state of the processor, right? It's only stuff that goes into my pipeline registers, which are microarchitectural state. I hope you remember very well the difference, right? Architecture is what is seen and understood by the programmer. Microarchitectural is what is just my business on how I'm doing my processor. So decode and fetch and decode affect only the microarchitectural state, as opposed, for instance, to memory that could write in the memory, so do something that the user can see, or write back that writes in the register, so again, something that the user could see in case of interrupt. Here I don't do any damage, so that's why it is easy. And what I do is that as soon as I figure out that I made a mistake because the branch was actually taken, I just nullify at this point, not before, as I said in the previous slide, which is a little bit too careful, maybe, right? I can wait until this moment to decide that I nullify and I squash these two pipeline stage at the end of the fetch and at the end of the decode, to say, no, that stuff is actually rubbish. And if it turns out that the branch was not taken, I have already the fetch and decode that did their job, and everything is ready, and so I can continue. Right? So this is a first very simple example of speculative execution that corresponds to a prediction that I actually cannot change, is static in the sense that I'm not trying to learn anything, it's just implicit. And the prediction is that typically a branch is not taken, right? So if it is not taken, I speculatively fetch and decode, and I'm right. If it is taken, I'm just doing the wrong thing. And for instance, if you think about it for a second, it's very difficult to say, oh no, but I think usually branches are taken, so I would like to predict statically that branches are taken. It's much more difficult to do. And we'll come in a minute to that in a few minutes, but we'll come to the point of saying, okay, how do I manage to fetch something that is not the next instruction, right? Here I have in the decode stage my branch, so during this time, I'm figuring out that, oh my God, there is a branch, and a priori is not very easy to say, while I'm discovering that there is a branch, I'm already fetching something that is the destination of the branch. Because of course, you understand, it seems impossible sort of to do, because you don't even know that it is a branch, right? All right. So, okay, this is what you have seen probably in your bachelor course already is one way to handle control hazards in simple pipelines. But the beauty is that we can do something much, much more powerful now in our much better architecture, out of order, dynamically scheduled superscalar, by using the ROB in a different way. So doing exactly the same thing that we have done for the exceptions, but adapt it for the branch. And what we need to do is to insert the branches in the reorder buffer. Now, this is a novelty, right? Because we had absolutely no reason to introduce the branches in the reorder buffer. Well, I think maybe I never mentioned it explicitly, but if you think about it, since the purpose of the reorder buffer is to affect the architectural state of the system, of the processor, and of the memory, only things that affect this state should be in the reorder buffer, and the branch doesn't do anything, right? It doesn't write to memory, it doesn't write into a register, and if we don't speculate about a branch, there is absolutely no reason to have it in the reorder buffer. But now we want. Now we want because we want to speculate and we want to have it in the reorder buffer as essentially a barrier, a separation between the part that is to be committed anyway because it's before this prediction, and the part that is below, which depends on the correctness of my prediction. So we want to have this in the reorder buffer, and we want to memorize what is the prediction that we have done. So we have predicted that the next instruction, the correct next instruction, is this 111 whatever. And you see it here, that is actually what we have done, right? Certainly this kind of structure is conceptually correct, but implementation, in terms of implementation, is probably not optimal in any possible sense. But you see here that the instruction that is after this branch at this PC is actually an instruction that has been fetched at these addresses. So for some reason, and we'll come to this later, but I have decided to predict that this branch is taken and is taken to this target address. And of course, I don't know what is the current address right now. So what happens? It's the same thing that we will do in the case of exceptions, right? We keep committing all the instructions that are before this branch until we get to this branch and we have the information of the destination. So for instance, if in this case I come to the point that I would like to commit this branch, but I don't have the value. First of all, commit is in double quotes, right? Because again, there is nothing to be done for committing a branch. But if I don't have, if I have not resolved yet whether my prediction was correct, I keep it there and I don't advance basically the reorder buffer. When at some point I get the information because whatever the branch decision needed to be taken, some computation, some equality or particular relation between two registers and so on and so forth, when I know what was the outcome, I put the value here and I look at the time of commit. I'm ready to commit. I look if these two values are the same. And if these two values are the same, it means correct prediction is the equivalent, if you want, of the moment I'm committing a memory instruction and I look at the exception bit to see if there was no exception, which was a correct prediction. That is, I correctly thought that there will not be any exception. Here is the same thing. I have this instruction and I'm asking myself, did I correctly predict? Now I compare the two values that I have. If they are the same, I commit, and note that the committing in this case, I said it many times already, I think, is doing nothing, is just moving to the next, moving the head to the next instruction, because there is nothing that the branch has to do to the state of the machine, right? But it's just that this separation becomes irrelevant, right? We have gone into the rest of the word of the program, and everything is fine. And of course, the other thing that can happen is that it turns out that this branch was not taken. The correct instruction to be executed after would have been just the subsequent one, the one following this branch, right? 4 bytes later, there is the C. So it's the next instruction that I should have executed, but I did the wrong thing. And what do? Again, exactly the same that I do in case of exception. I commit, or I take out, whatever is the expression that you like, this branch from the queue by doing once more nothing, except that I'm going to squash, to throw away anything that was past it, so that now nobody will ever know that I made a wrong prediction and I computed values, right? If you've seen a minute ago before the comparison, right? I had already a number of values that were completely executed, computed, and probably reused inside my machine. All these things nobody will know, because I delete everything and I restart from scratch, which is I take this value and I send it into the fetch PC, the PC in the fetch unit, and I start taking the instruction, whatever it is, 10 million, whatever C, and I take this and I restart from there. Okay, so it's great. So the speculation comes essentially for free, right? What you are seeing is nothing else than a slight cosmetic change or extension of something that we were doing already. Now, there is a problem that is also very interesting and, in a sense, more new, which is the problem of the prediction. It's less trivial than the case of the exception, where again we have a very static prediction that is almost certainly right. There is no exception. And now we need to understand what to do. Now, there are some techniques that people have used only for a few years until they improved things significantly and they moved to the world of the dynamic. So there are some techniques that are just invariants, so sort of we assume that some instructions do have a specific target that is more likely than the other, and some cases that are, and we will focus mostly on the dynamic case. Just to fix and clarify the problem, what we have available and what we need to do. So there is some logic, some hardware that we are going to potentially put. Again, in the static case, maybe this hardware is extremely simple or inexistent. In the dynamic case, it will be maybe pretty important part of the processor, and maybe in modern processor is actually also one part that in the processor inside the core has a relatively important energy consumption, because it does a lot of let's say calculation of some sort. And what does it take as an input? What is the visibility that this logic has? But typically it knows where we are, what are we trying to fetch, and the PC is available before the fetch, right? As you can easily understand, right? The moment I'm using the current PC to go to memory and fetch, I can already know that, okay, we are going to fetch that instruction, right? Which we don't know what it is, but we know that it is the instruction at a specific position in instruction memory. And of course I have, because I'm somewhere in the processor, I may have a lot of information about the past. I can observe what happened in the past. And typically what I can observe is what happened of previous branches, right? What is the history? And I need to do a couple of predictions that in some sense are the same. I need both predictions to do to do branch prediction, but somehow they are two different problems, and maybe the hardware structure that we are going to use are different. One is the prediction whether we take or not take a specific branch. What is the target address of a branch? Are we going to go there or not, right? So is the typically in a branch equal, are the two registers that I'm going to compare typically equal or not? And of course, I don't know, but I may try to learn from the outcome of previous cases whether it happens or it doesn't happen. And the other, so this is a binary decision. And the other is to know what is most likely the target address. If it is a branch and is a branch R1, R2 loop, the target is loop. And what is this loop? What is the address of loop? So the first thing that you can ask, but maybe it's already self-evident from some of the comments before, is why do I need to predict the target address? Right? The target address is always, maybe not always, but most likely written inside as an immediate inside the instruction. And this goes with something that we said a few minutes ago. I think I said it in the case of the simple pipeline. I just fetched the previous instruction, and now I would like to do another fetch, and I would like to fetch potentially already the branch. And I haven't had the time to decode the previous instruction. So the previous instruction that I have fetched, I have not even an idea that it is a branch, and even less what is in this branch the target address, where typically also maybe is a relative branch. So I have an immediate, but I need to add this immediate to the PC so that I can find the absolute target. So maybe I need still to go through an adder before I know this. This, I would like to have it way before I even start to decode the previous instruction. So this is the reason I want to predict also this, that you may think is available relatively soon. This is clear that in many cases it will take even a lot of time, right? If I'm comparing or something that is the result of a previous operation, maybe is a load, is a miss, it will take 100 cycles. Maybe I have 100 cycles before I know whether a branch is taken or not. This one seems to be immediately available, but I actually want it even earlier than I will have it available. So let's start from this target address prediction. And there is a very natural way to do this, which is to say, let's take the PC where we are fetching instructions, and let's try to remember in a new data structure that we call branch target buffer. Let's try to remember when we have seen that they fetched the instruction turned out to be a branch with a specific target address, and let's memorize also what this target address was. So the idea is that this is essentially a CAM, a content address memory, where every time I can go in and look at the PC where the rest of the architecture is going and fetch an instruction, and while it is being fetched, I look if I see this PC, this value in this part of the table. If I find it, I can predict that the target address is going to be what I see here on the right. And except some cases, one in particular will come back later, a bit later today, but in most cases, this is going to be a very good prediction, right? Because if I fetched at a specific program counter, a specific branch at a given point in the execution, it's very certain that if I go and except very extreme cases, but is almost certain that what I'm going to fetch the next time at the same address is going to be the same branch, which will have, by construction of the instruction set, probably the same target address. So this is a fairly good prediction. You can see these branch target buffers as essentially a sort of a cache, right? It's not a cache that memorizes the memory content, but is a cache that memorizes the target address that have been seen recently. And like a cache, you're going to treat it, right? For instance, at some point, of course, this is a some that you have some space in this buffer, and at some point this buffer will be full. What will you do? The same kind of things that you are used to do in caches, right? You'll say, okay, let's take one of the old branch addresses, for instance, the one that I have least recently used, so the one that seems to be not particularly useful in recent times, and you'll replace that entry with the new entry that you are observing right now. And so you'll try to keep a number of recent branches that you have visited in such a way that you can predict that they are branches and that they have a specific target address. And if the companion part of this target predictor will tell you that it's probably taken, you'll take this target address, and before you have even started to decode the instruction that you're fetching, because all this is completely independent from the fetching and decoding of the instruction, you will predict that the next address to fetch is going to be this, and so the next cycle you'll be ready to go. Now, I said that this is essentially a bit like a cache, and I hope you remember caches. Again, it's something that I assume that is well known from your bachelor courses. If it is not, take this opportunity to go and revise. There will be a few allusions to caches today. But the first thing that I can do is that this is a one form, this version of this structure corresponds to one form of cache. I would want to do a break, but I'm going to spare it from you, but you can still stop if you want. Which kind of cache this looks like? This looks like a fully associative cache, right? This word associative comes out very often in doing this kind of hardware. What does it mean? It's fully associative. It means that I have essentially a comparator that is not shown in this image, but I have a comparator per line, per entry of this buffer. And these comparators in parallel, when they are exposed to the current PC, in parallel, they say, oh, is this PC this address? No. Is this PC this address? Is this PC this address? And all of these comparisons are done in parallel. So these kind of structures, and of course, the hope or the mechanism is that at most one of these will be equal to one, will be through the comparison, because I'm very careful not to put the same branch address twice in this data structure. Now, if you remember from the time of your studying the caches, this is an extremely expensive structure that also very often doesn't pay off. It's somehow the best cache that you could do, except that it's very difficult to implement, and especially it's very difficult to implement a large cache. So typically people don't really implement it this way. And so any of the games that you know for caches are possible for these branch target buffers. So the classic organization that you know very well for a cache, like this will be a two-way set associative cache, well, you can do a two-way set associative branch target buffer where you use part of the address to address a normal memory, not a content addressable memory, but a normal memory. You can store in this structure the rest of the address, so which we call the tag, in a different sense than the tag that we were discussing in the last weeks, but is the characteristic, the remaining part characteristic of that address. And the idea is that for each of these ways, for each of these memories that operate in parallel, in this case we have two, but we could have 3, 4, 5, whatever we want. The way it operates is that we go in with this index, we get one of these elements with these entries, and we take out the tag, we see if the tag is correct. If the tag is correct, then this is the target address that we wanted. So we have compared completely. Is this why did I say that this is a worse structure than the previous one, or a worse cache than the previous one? I'm sorry to say this, for many people among you, maybe these things are totally clear, but I'm sure there is maybe someone that is a bit sort of has forgotten a little some of these things, so I prefer to repeat. Why is this a little bit worse, or worse than this structure? Because here, for any PC, I have n possible places where to put it. Whereas in here, for each PC, for each value of the program counter, I've only two places to put it, because depending on this value, I can put it here or here at my choice, but there is one part that I don't control, which is where it goes. So depending on the address, which is not under my control, if it is 0001, it can only go here or here. So I have much less flexibility, or a much higher likelihood of collisions. For instance, if I have my branches, 3 branches that end by 00001, I can put one branch here and one branch here, but I cannot have a third branch at the same address that I can predict with this branch target buffer, because it will collide, as we say, with these two, and I will keep ejecting or evicting one of these two to make place for the third, and then again and again. Only two I can have the information, which is completely absent, is a limitation that is completely absent here. I can have all my branches that are at an address that ends with 00001. There is no problem. I can have n of them, and they will be perfectly fine here. Okay, this is something that I hope you know very well, again, from caches, is that the practice is that usually this is a relatively minor issue, in the sense that sometimes it will remove some of the potential of using this structure compared to these structures, will make it less useful for you, but it makes it hugely more easier to implement, because here there is one comparator here and one here that is not shown, but I hope you understand is there. So there are two comparators active at the same time, instead of say 1000, if there are 1000 of elements in this structure. So whatever you know for caches and organization, you can apply to the branch target buffers, and I hope the general idea of what they operate and why, it's clear, right? Again, I see in parallel to the fetching that that thing was most likely a branch and had a most likely the target address buffer that the target address that I have observed in a previous execution of that instruction. So now we have the other part, which is it taken or not taken? Is this really the address that we have to execute, or most likely this branch is not taken? And again, we can do sort of the same thing, right? We can use the PC, the characteristic address where this branch comes from, so the identifier, if you want, of the branch in my program, and try to remember what is the last thing that we have seen about that branch. What is the last outcome? So forget for a second the 2-bit prediction. We'll come to this in a moment, but just to make things simple, think of the 1-bit prediction, which is the last thing that we have been here in this branch. It was not taken. So next time that we come here, why don't we assume that maybe it will be the same and still not taken? So this is the sense of this structure, right? I take the branch address, I take a part of it, is an index, I go and I index inside here, so I read in normal memory this value, I see if it is not taken, I assume that this is probably the prediction, the correct prediction that I should do. Now, you should be puzzled by something, right? Because I'm saying we do the same thing, but I'm not quite doing the very same thing that I was doing for the address. And I want you to stop for a second and think what is missing in this figure that was not missing in the previous one. What distinguishes this greatly from a cache? Again, we're not talking of data cache memorizing the values of memory, but what in the structure of this is different in terms of looking at the last time that I've seen something compared to what we were doing a minute ago about the target address and we have been doing forever in a cache. And the problem is what happens with those other, in this example, other 24 bits. What do we do? Naturally, there we had a tag. And if you remember what I described a few seconds ago in the other image, right? We take them to look whether the rest of the address, not this, I memorize the rest of the address in the same data structure. And I see if it is the correct one. If it is the correct one, I think I found my information. And what I'm doing here is, in a sense, terrible, because I'm not even checking if what I learn here is exactly of my branch, because I looked only at part of the addresses, but it might be a completely different branch, and I will never know. Now, there is a morality from this that is extremely important. It is the fact that the moment we are trying to predict, that we are trying to make a good guess, some types of mistakes that may not be very common are irrelevant to us. Now, I hope you stop for a second to think about this, right? In a cache, I'm not doing any prediction of any sort, right? I'm trying to check if what is in my cache is the value that the processor is asking me. And I'll figure out if I have it or not. So I cannot make mistakes. I cannot give something else saying, oh, probably it's this one, take it. So I do have imperative need to have the tag. It's not because I try to be good. It's without a tag, a cache cannot work. Here, we are in a different world. We are in a world where I'm trying to be right. But actually, maybe I'm not. And if this doesn't happen too often, who cares? For instance, here the problem is the fact that I have collisions. I may have a branch address, I may have two branch addresses that are at an address that finishes with 8 bits at 0. I might. It's not terribly likely. It's certainly possible. It will happen in some cases, but it's not the most likely thing to happen. And therefore, I can ignore the problem. Think about it, right? It brings me in a completely new world, and I insist on that and I repeat that because it's the reasoning that I can start doing is completely different. For instance, follow me in this. Suppose that I need to put the tag, right? When I have the tag, if I want to avoid telling you the wrong taken, not taken, what I need to do is to add the tag, right? So let me go back to when I had space on the left so that I can annotate a little bit this, right? If I need to add the tag goes here and is an equivalent memory. Sorry for the drawing is always a little challenging. I need to add these tags to in this memory, right? And I need to put in the tag 24 bits of data, just taking the numbers from this example, right? So somehow in terms of storage, my storage that contained, apart from doing comparison and these kind of things, which of course is not a big deal, so I can do the comparison. But in terms of storage, where I had 1 bit, now I have 25, right? So I'm doing a structure to correct the problem that I had before and now be absolutely sure that I'm telling you the not taken of the branch that you wanted. I need 25 times more storage. Now, again, in a cache, this is the only thing that I can do. There is no other way. But now we can ask ourselves, in this situation where I am allowed to be wrong, is there something else that I can do? And of course there is, and I hope that some of you see it. What I could do is to say, okay, if you give me more storage, let's say you give me 32 times more storage and I'm just rounding it up, is sort of the same thing, right? I'm rounding it up because I need to have a power of 2. If I have 32 times the storage that I had before, what I can do is to do this structure much longer, right? Instead of doing it fat, right? Instead of widening this memory, I don't do that, and I do it longer, and specifically 32 times longer, which means that there are 5 bits more of address, right? There are more address bits because it is longer. And so this doesn't cover only to the 7, but to whatever it is, the 12 bit. Okay? This has partly the same effect. It's not perfect. Again, it's something that remains in the realm of things where I may be wrong, but reduces the probability of collisions, right? Now, maybe 2 of the addresses that were colliding had all zeros at the end, but now there is maybe one lands here and one lands in an address that is 0, 0, 1, and 8 zeros. You understand what I'm saying, right? Maybe the 2 addresses that had the same lowest 8 bits don't have the next 5 bits identical, and so now land in two-bit predictors to 1-bit predictors that are completely different, so I'm giving you the right value. Again, I am in a sort of predictive, possibly wrong situation because maybe actually they are 2 addresses. I'm particularly unlucky that have the last 12, 13 bits, whatever it is, that are exactly identical, and therefore they still have a collision, and I'm still giving you the wrong information for that branch because I mix up 2 cases. Simply the probability, if it were uniform, if the probability has gone down by a factor of 32, which is an important factor, right? If it was 10% before, now it's 0.3% probability. So it's really nothing. Again, under the hypothesis that addresses are uniformly distributed. In fact, probably it helps me the fact that they have correlation, because probably many of the addresses are relatively close because they are part of my program, and so maybe actually they tend to be to my favor. I've even improved more than that. Okay, this is something that I could, because I'm still potentially wrong, just less frequently wrong, that I could not have done before. Now, they cost more or less the same. Is there an advantage to do the blue or to do the pink here? Now, think about that. With the blue, if I'm wrong, I am. If I have a collision with the blue, I can be precise but silly in a sense. I can tell you, I don't know the prediction. I know it exactly with incredible precision, perfect precision. I can tell you, I have no idea of your branch. Great, thank you very much, right? And now what do we do? Here, if I have a collision, if I had a collision before, one of the collision that I had before between this address and this address that would have collided before, for one of the two, I would have said, I have no idea. Now, both of them are learning about the branch. So I have actually traded total precision in telling you that I have no idea for I still make mistakes, but I have 32 times more probability to give you the right information, which the blue part doesn't do for me. It just tells me I don't know, but it has not more information about branches. I hope you are, again, spending a few cycles in your brain to think how powerful it is to be in this world of prediction and speculation. Point is, blue is the only thing that in an exact word you can do. Pink is a totally new word that you can do now. And it can be much, much better. In other words, what you can do is that if there is something that happens extremely seldom, you can ignore it and go ahead in a much more expedite way, assuming that it will not happen. And if it happens, bad. Now, if you think of it and you really stop and think of it in your experience, also when you do programs, when you maybe create hardware, if you have some hardware design experience, most of the complexity of the additional things that you have to do and spend time on are the special cases that sort of never happens, right? I'm going through a gigantic array bidimensional matrix, and I have to do some special code for when I'm at the beginning and at the end. But most of the time, I am not at the beginning and the end. Most of the time, I'm in the middle of a row or of a column or of my matrix or of my image. So having this notion of speculation and so on means do things as they are in most of the time and ignore all these special cases. You'll come back and correct only in that special situations. And we'll see a case very soon in a few slides. Another case is still related to branches, but it's another thing that we would like to do in our processors, and it's actually natural and almost never wrong, except that it is not always right. And therefore, we do things that are much more complicated for that special situation where it doesn't work. And it's great to be able to ignore that special case and try to go ahead so that most of the time we gain a lot of time and very seldom we'll have a setback, but that will be not a big deal. All right, what we have seen until now is how to find my predictor, my correct predictor, my appropriate predictor. Now we can spend a little bit of time on understanding how to create these predictors, this 1-bit predictor, 2-bit predictor, or more complicated one. It's an area that has seen, especially a few years ago, a huge amount of research. I think there is actually some resurgence of interest in research in this area. You'll see in the next few slides, I'm going to describe some of the typical cases that they are a mixture of intuition of what might happen with my branches in my program, plus sometimes something that is very hard to make sense of, but which turns out intuitively and in practice to work well. There is a lot of what I call cuisine, in the sense that it's just cooking, right? You just put together a couple of things, it works well. Okay, so then why don't we put it also together with another ingredient, and it works even well, even better, and so on and so forth. So I don't think it is terribly important to have, unless you need to design one of these predictors, I don't think it is terribly interesting to go into every detail, but I think it's nice to have a little bit of exposure to the different things that can be done. And what we have seen so far, what we have described so far, which is to remember what is the last outcome of a branch, or what actually happened of a specific branch last time that it was seen in the execution of our program, corresponds essentially to this finite state diagram, right? Where I have two nodes, two states, the 1-bit 0 or 1 that says taken or not taken, predict taken or not taken, and depending on what happens, so the annotation on the edges, I move or I stay in a given prediction. For instance, I predict not taken if it is actually, it turns out later that it was in fact not taken, so I was right. I keep myself believing that is not taken and predicting it not taken. If I was mistaken, I go and move in the other state and I go into taken. Again, this is totally a silly finite state machine, because it simply says take the outcome and put it into the 1-bit that you have. But it's nice to look at it this way, because what you actually want to do, or may want to do, and actually what everybody does, plus many other things, but the minimum that everybody does is to adding a little bit of inertia to this system. So one way that you can also describe and look at this finite state machine is a counter, is a 1-bit counter that saturates, right? You count 0, 1, and then the next one is saturated 1, 1, 1, 1, 1, right? Or you decrement to a 0, and then you decrement and you stay in 0. Now it's very silly when it is 1 bit, is a little less silly when it is 2 bits, and this is what happens, right? Every time that something is taken, you increment the counter, and when you arrive to the maximum, you stay there, and every time you decrement, you go down until you are at the minimum and you stay there. And why it is interesting to have a more than 1-bit counter, again, I said the word, is that it gives you a little bit of inertia, right? If I am here and I say not taken, and it turns out that I made a mistake, it was actually taken, I go in a different state where I still say not taken. I still predict that is not taken, but if I'm mistaken a second time, then I'm really convinced that I need to say taken. So I need to mispredict twice before I convince myself of changing my mind. And if it turns out that the second time that I say not taken is actually correct, I come back to this sort of deeper state. And typically people call this a strong prediction of not taken, and call this a weak prediction of not taken. Now, what is the intuition behind this? This is one of those cases where there is an intuition of why it may work better, the 2-bit predictor, right? There are 4 states, so this is a 2-bit predictor. Why it may work better is, for instance, a program like this. So suppose that you have two loops, one inside the other. I'm sure you have seen this, or you have written some code like this. And what happens of this internal loop is that, of course, is depending on however this is written in assembly, but suppose that there is a branch equal to the beginning at the end of this iteration. So it's typically taken for call -1 times, and then once, when we are at the end of the loop 2, it's actually not taken and it continues. And next time that we come here to this branch from the next outer iteration, it's the same thing. The first time it will be taken because it's for j equal to 0, and then it continues to be taken for call -1, and the last time we go out. So there is always one case where I go out, and there is no way that with a simple predictor I can learn that, right? I will be mistaken that time because it's normally taken and once is not taken. But if I do it with a 1-bit counter, with a 1-bit predictor, of course I mispredict twice. I will have learned that it is usually taken. I arrive here, the last iteration, and it's not taken. Oops, first mistake. But now I learn very quickly because I'm very responsive, right? There is no inertia that I should predict not taken. When I come back in this loop and I'm here again, the first time that I come here, I say, well, not taken, right? Because that was the last time. But it's wrong because now I have to take it for call -1 times. And so again, I mispredict once. So I mispredict always the first and the last iteration of the inner loop. Now, since this code is very typical, maybe it's a good idea to have a predictor like this that actually, when I see that I say it's always taken and there is a not taken situation at the last one, I go here and I keep predicting taken. When I come back, I'll keep predicting taken. It takes more than one misprediction to convince me to change my prediction, right? So it's a simple example, but it's the intuition behind the fact that, for instance, 2-bit predictor is better than 1. Now, people have done more exotic things, and there we go in the space of, I honestly, if you ask me, maybe someone else knows, and maybe there is, but I'm just ignorant enough not to know. What is the intuition of this change? That they do a state machine that is slightly different. It has the same notion of it takes twice a mistaken prediction to convince me to change. But the funny thing is that I get not convinced to change to a weak prediction of the other side, so a weak reversal, like in the case that we just described, but I go and I do what is people call, I think, a strong reversal. I convince myself that I really, really, really should say taken, and I will not change my mind again unless I predict twice. Now, why is the second one better than the first one? I know that some processors use this one instead of the second one instead of the first. They used it in the past, maybe they use it today. I'm pretty sure that Intel doesn't tell you very precisely which method they use. There is no intuition, right? I think there is not intuition. Maybe I'm ignoring in this case, but I think essentially what happens is that you take your benchmark, you take your simulator, you try to put whatever prediction and state machine that you can, and you see if it works. If it works on average better the second, you take the second, and that's it. Now, you can do things that are a little bit more sophisticated, but before looking at that, it's interesting to understand how good we tend to be with this. And here you have 3 cases. The first case is you have 4,096 entries of these 2-bit predictors. So when I say 4,096 entries, I mean the log of 4,096 is 12. I mean 12 bits of the address bring me in this data structure where I find the different predictors, right? And the second one, the second bar that we are going to look at in this graph, are the same situation, not physical, but done by through simulation, of course, because there is no way to implement something like this physically, where you have unlimited entries. So you'll never have collisions, never any problem of not getting the right prediction from the right predictor. And the third one is what we are going to see in a minute. And what you see is that they do a pretty reasonable job, right? Especially if you look at I think there are two comments that we need to do. First of all, or maybe even more. One is that between the 4096 and unlimited, there is almost no change. I think I see one change here, and is probably and some changes in these situations where there is almost nothing, which goes well with what we were discussing before, right? The unlimited entries is not a physically possible situation, but is a situation where I would have tags and make sure that I always have the correct prediction for you. And here is a reasonable prediction with some potential of collisions. And what we see here is that collisions don't create too many problems. So that is one very, in a sense, a very positive observation, right? We can get away with a relatively small set of predictors and everything goes well. Another thing that we can observe is that there are in some applications like these, which are numerical algorithms, essentially not very dissimilar probably from loops of this sort, relatively regular, precise for loops, predictions are, everything is predicted very well, right? Matrix 300, I think it does some linear algebra on matrices of size 300 by 300. And so I mispredict only once every 300 most of the things, so everything is perfect, right? Another comment is that what we will do in a minute brings down, even in the worst case, right? This is the worst case. What we are going to do in a minute brings down the mixed predictions so that almost in every case, the number of misprediction is relatively low. We will try to get a perspective on what it means relatively low a little later, but still, I mean, 95% of the time I'm guessing well, which I think is in absolute terms seems to be a pretty reasonable result. Maybe last observation is that not for everyone, right? For instance, this technique that we are going to see in a minute is dramatically improving, right, by more than 30%, 60% or something like this. Some predictions does almost nothing in the one that becomes the worst program, right? These are a set of benchmarks and a set of actually practical programs that represent or are supposed to represent how people tend to use processors. And you know this program very well, right? It's GCC, so it's a compiler. And it's interesting because it means that a compiler has a sort of such a diverse code base, is doing so many different things, and the outcome of the different things that are done while parsing the code, while generating the assembly, scheduling the assembly, the outcome is so unpredictable that intrinsically it seems extremely difficult to lower its misprediction. And is the perfect opposite of these kind of cases, right? Where I have nice loops that I know exactly how many times I have to do. So it seems natural that I can do better. But unfortunately, it's a bad news that I cannot do any better than this. And again, maybe later we'll do a little computation to get a sense of how bad this is. since I just mentioned again the problem of the aliasing and how aliasing is or is not important in the graph that we have just seen with the number of mispredictions or the frequency of mispredictions, it reminded me that there was something that I wanted to observe and ask you a question and think about. We have omitted the tags when we were doing the 1 and 2 bit predictors to try to remember the history of a specific branch, right? And we said, oh, we don't need the tags. We are in this beautiful new world where we can be wrong. So screw the tag and forget about it. Now I wanted to go back to this. So we have the branch target buffers, and here we didn't decide to get rid of the tags. So why is that? And I want to do a pause so that we have you have a second for thinking to think about it. So why did we keep the tag in this situation? I think there are a couple of reasons that we can think of. One reason is that here, what I'm storing in the data part of this sort of cache is the target address. So it's a much longer, in terms of number of bits, piece of information, right? It may be, I don't know, 32-bit, 24, 64, whatever it is, right? In a x86 these days, it will be a 64-bit. What does that mean is that the tag, this part of the storage compared to this part of the storage, is almost certainly shorter here, is actually certainly shorter here than it is here. Or in other words, if I suppress this and I decide to use this value, this part of storage to increase the length of the data storage of the target address part of this table, at most I can double it. So part of the reasoning that we had before, that I can, instead of putting the tag, I may do it 32 times bigger, that kind of order of magnitude absolutely does not exist in this case. That is perhaps one reason for keeping the tag here. There is another one. If here I make a mistake and I confuse two different branches and I get the target address of the other one, I'm almost certainly to be badly wrong, right? And there is little chance, it may happen, but there is little chance that two branches that happen to have the last n bits to the same value actually are branches whose target address is exactly the same. So if I make a mistake here, it's particularly bad, right? In the sense that I'm almost sure to be wrong. It's slightly different in the case of the predictors, of the history buffers, because in that case, the information is binary. So if again we assume that everything is uncorrelated, which is wrong, but is at least useful for us to think about, I get some prediction, and this prediction is at most 50% wrong. So it's less bad to not realize that I had an alias. In that case, I can still take it for some prediction, and of course it will be a much worse prediction because it will be based on throwing a coin rather than actually having learned something from history. Here, if I make a mistake, I really go into a place that it's wrong. And it's better to know that it is almost certainly wrong, because I have another option that is less unlikely to be wrong, which is to say, okay, if I have absolutely no information on a specific branch, well, let me not try to jump to a place that is completely nonsensical. Tell me, let me know, because I will fetch the next instruction. I still have some probability that the next instruction will be correct, whereas a wrong target is certainly wrong. So here it does help knowing, look, I have no information about this branch. Whereas in the other case, maybe it doesn't, or it doesn't give so much helpful information. Now, coming back to a couple of further improvements that we are going to do to our predictors, here is one of the things that also, in a sense, everyone tries to do, every processor tries to do, which is to do something that I'll describe first functionally so that we understand what this schematic represents, and then we'll try to think of why, what actually it does, right? So we are going to capture in a register, in what is a shift register, all the last branch outcomes or branch predictions that we have done for previous branches. And we're going to, as I said, collect it into a shift register. So what this means is that the branch before, so we are at some branch address, right? We are trying to predict something for a given branch that is under analysis in this moment. So the branch that was in the program before, whatever it was, 5 instructions ago or 20 or whatever it was, say, taken, and the branch before that one that we have visited was, say, not taken, right? So we have this information, and we use this information for choosing among 4 different predictors exactly like the ones that we have seen before. So each of these columns is a normal, say, 2-bit predictor, like the one we have seen a minute ago. So now we are going to have 4 different predictors in parallel that are going to predict potentially something different, and we choose which one to listen to depending on what happened on the last 2 branches. So stop and think for a second. What is happening here? What are we trying to do? Well, it's the title of the slide, right? We are trying to exploit correlation between branches. We are trying to learn that if the last 2, for instance, were taken, maybe this new branch is typically not taken, but if these 2 were not taken, this particular branch maybe has more likelihood to be taken. Now, one question that you can ask is, but first of all, I think it's clear that some correlation between branches might exist, but maybe we can try to concoct at least an extreme example. And one extreme example could be the fact that I have 2 branches, maybe one following the next, that are exactly under the same condition. Now, if you think of pieces of software that you have written, it might happen more often than you would like. So you do a test for a special situation that maybe happens only in some cases, and you do something special. Then you do some other calculation, and which happens in any case, so is out of the first if. And then you do again a if to test for the same special condition and do something else on what you just calculated based on the same condition. Now, again, this happens, right? Because, of course, you could have a different solution. I hope you are following my reasoning and you see in your mind the piece of code. You could write everything as a big if, where you do the test only once, and the central part, the one that in my example was out of the if, you put it also in the else. But you don't like to do that, right? It's better performance, but it's worse code, because now you have the same operations in the then and else of your of your branch, and now you're almost sure that when you find a bug in that one, you correct one and you don't correct the other, and so you're generating new bugs instead of really correcting. So it's pretty bad practice, except that doing the two branches with the same condition is performance-wise not very good. Now let's look at how this structure can help. Let's take a simpler version of this just to address the simple case that I just described. So let's take only one bit here. So there is only one bit of outcome. So only the last branch we are considering. So there are only 2 to the 1, that is 2 of these predictors. So these 2 don't exist at all. Okay, and so what happens? When this is taken, the specific branch, the previous branch, so the first one of my 2 predictors, of my 2 branches, the second branch, when I try to predict it and it will land on a specific entry of the predictor, if this is taken and this is not taken, it will tend to learn taken, right? Because it is under the case that the previous one was taken. Now, suppose now that this is not taken, the second one will also be not taken, so it will learn that is not taken. And now I have 2 correlated branches that may change all the time, may be very unpredictable. Now, I don't know anything about how much I will predict the first one, and probably I will do very bad if it is very unpredictable. But the second one, I will predict always perfectly. Because, again, depending on what is the value here, right, whatever is the value here, I'll take a predictor that for taken gives me taken, and for not taken gives me not taken. That is, consider that these 2 branches are exactly the same. And this is correct, and it will predict. Now, you cannot do this without this kind of idea, right? Without taking into some account, the outcome of previous branches. If I have a very unpredictable branch and I have the same a little later in my code, they will be both poorly predicted. So you can get the sense that this is intuitively a good idea. Now, there is a different way to see exactly this predictor. It's called a 2-level predictor, and is, by the way, the one that we have seen in the previous graph as the one that was improving fairly significant most of the cases where good predictions were not possible with the simpler predictor. So it's a very useful predictor, and it can be represented in a slightly different way. It's exactly the same, it's just drawn differently and maybe less intuitive what is happening. Is that, if you think about it, is the same thing of having 4 separate predictors and selecting which one based on these 2 bits, is to say, I take these 2 bits and I use these 2 bits as part, I chain them of the addressing. So I have these 4 bits that I'm taking from the branch address and 2 bits that come from this. I put them together and I go into a structure that is 4 times bigger than this. So if this was 16, this is 64, right? Which is exactly addressed by 6 bits. So again, this is a cosmetic redrawing. I think that the left one is much more useful for me as a human to understand what the heck is happening. The right one is less understandable, but is exactly the same thing. Based on this sort of observation or this way to represent it, one could think of doing something else. And the something else is to say, instead of hashing, because this is a form of hashing, right? How do I combine these things to go and read into my branch predictor? And I do it by just juxtaposing the 2 pieces. I can do some other more sophisticated form of hashing. I could do XOR of what comes from the branch address and what comes from the outcome. The advantage, for instance, is if I have 6 bits here, is that I can take more bits of the branch address, and I can take many more outcomes because I want to have these two equal, because I want to XOR all of them. So I take much more history and many more bits of the address, which helps with the aliasing, as we were discussing before, and I XOR them, I hash them, I try to get some mixture of them to read the branch predictor. Now, this predictor is actually also a very popular predictor. It's called the G-share, and the person McFarlane that invented the G-share predictor called the G-select, the previous predictor that we have seen. This G-share predictor is much less intuitive what exactly it does. Like anything that is based on complex hashing is hashing, right? It's just you are going to search with some non-trivial function from your entry elements into a data structure, but although less intuitive, it may work better. And in fact, it does work better, I think, essentially because the hashing avoids typical and trivial collisions, and yet at the same time, you are using more information to distribute your prediction or your predictors across a battery of predictors. So this is as far as we are going in this prediction game. Actually, real predictors are probably reasonably more complex. You have some examples in the Hennessy Patterson. It's also something that I believe no manufacturer of processors is very happy to tell you in great detail, because it's part of sort of the secret of their technology, right? Of their processor. I want to mention a couple of extensions without going into too much detail, and I'm not doing even any drawing for. I think the second one, there is a drawing in the Hennessy Patterson. One is tournament predictors. Is you can say, okay, let's do different type of predictors. Maybe some are local, some are global. Global means they try to take into account correlation and so on. And let's try to have a selector that decides among these predictors, let's predict which one is right for a specific, is correct, is appropriate for a specific branch, right? In some sense, I think you can see it as an extension of this idea of the multiplexer, right? Sort of you have here not just the outcomes, but a predictor that says, which one shall I use? And multiple predictors that maybe function on really different principles, not like here, sort of identical predictors, but different predictors. And you decide that based on some, on the experience, the first predictor, the local predictor, seems to be good for this branch. And maybe for another branch is actually the other very complex predictor that works better. Now, one of the things is also interesting is that I think it's interesting to notice is that the more you try to do these wild things that make perfect sense, right? But then it becomes very difficult to decide, for instance, how you update. Now, the moment you mispredict, so you have used this system and you have a misprediction, now what do? You are going to change the selector and figure out that the selector was not suggesting the right predictor, or is the suggested predictor that should be updated because maybe it was not predicting in this particular case the right thing, but could have done better, or both? And I think if you think for a second, it's absolutely not clear what is the right thing to do, right? So it becomes a very complex word where I don't think there is a correct answer, but there is only the fact that statistically and heuristically, there are some things that work better than the others. So this is where the cooking part comes in the picture, right? You put together the different pieces and you see how it works. The other trend that I think is useful to mention, but we are not going to look into big detail, is to actually put the tags, right? Put some tags back into the predictor so that you avoid aliases as much as you can, and you try to make repeatedly a tagged predictor. You look into one way and you see if you found the exact predictor, and if you haven't found it, okay, you look into another predictor and you find maybe again with a tag, and you say, okay, I found exactly the predictor for my branch, and so on and so forth, until at some point you give up on finding exactly the predictor you want, and you take a generic predictor that is available, and maybe is aliased with something else, maybe is something that you didn't bother, or you didn't have space to tag in the other predictors, right? So you try to be exactly precise if you can, and make sure that you get the right predictor. And if you can't, you still are in the world that you say, okay, but let's take something else that maybe is right or maybe not. So you try to correct partially the precision and the aliasing problem in very specific situations. Okay, this was a longish detour on predictors. We are almost done on, sorry, not predictors in general, but branch predictors. Remember that, let's zoom out, right? We are talking of something much wider than just predicting branches, but now we have spent a relatively longish amount of time on one of the easiest, or maybe more interesting or more classic type of predictors, that is the branch predictor. Before abandoning it, I want to do one more thing in the area of branch predictors. And I want to do it with one of the questions where I stop, and I invite you to stop and think. The question is the following. There is a situation that we all know extremely well, where these branch predictors that we have seen, especially the branch target buffers, are going to fail miserably. They have almost no chance to, I'm exaggerating a little, but they will never be right, or almost never be right. I hope it is clear, the problem, right? So we have understood, I hope, how to do a branch target buffer. Just remember the last address I went after this instruction, and this instruction is clearly a branch, right? And the next instruction is something, and I remember, and almost never I go there. So what is this situation where this happens? And again, I really want to do a pause, because you need to think about it a little, because you absolutely know exactly this kind of situation. Maybe you haven't realized how bad are our predictors in that case. So did you find it out? Well, the case is clearly one of those cases where the destination is not an immediate value in the field of the branch or of the jump, right? If it is an immediate value, of course, it doesn't change. So clearly what I've done until now was a good choice. So there are two situations where this happens, and actually maybe if you know MIPS, the first one helps us identify the second, which is the one that is interesting to us. In general, it is when it is an indirect branch, right? So if I speak MIPS, it's instructions like jump register a specific register, right? And in a sense, there is little that I can do to predict that, right? Because if it is an indirect branch, and if it is an indirect address, well, I mean, it depends on the value of a register, and it's extremely difficult for me to have a sense of when this happens, what is the value in the register. Except a case that, as I said, it helps to think in terms of MIPS, which is a typical case of an indirect branch. So if you know jump register as an instruction in MIPS, you know exactly one case, maybe the only case you have ever used in exercises in your bachelor course or so, you have ever used this jump register instruction, which is what? Which is the return from a function, from a subroutine, right? You have the value somewhere of the return of the callee, of the caller, so of the program that called you or the instruction that issued the call. You have the address of the instruction that follows the call somewhere. If you are an x86, you have it on the stack somewhere. If you are a MIPS, you have it into a register that is called RA, return address. Clearly, both the jump register, $array, return address, or the return are indirect branches, indirect jumps to a different part of code. So intrinsically, they belong to this category that we can predict because somehow they change all the time. At the same time, we do know a lot, especially if it is a return, like in a x86 kind of processor. We know exactly what this instruction is and how normally people use this instruction. And so we can try to exploit that. So what we know is that there is a stack, right, somewhere. So let's focus on the call and return on an x86, right? There is this stack in memory that contains something. And what we do is that we are going to, whenever we do a call, we add on it the return address. And so we push the value of the return address on the stack. Maybe we push some other stuff later. We'll take it away at a later time. And by the time we are ready to issue the return, there is nothing else than the return address here. And now we issue a return instruction that takes it out and does a jump to this. So we understand very well that there is these two instructions are used in pairs. Actually, they are in different parts of our program, but they are always used in pairs, right? One pushes on the stack, and the other takes away from the stack. So there is a absolutely natural idea to have, I hope, which is to say, why am I bothering to put it on my memory? This is my memory, right? And actually, one thing that is in particular horrible is that whenever I do a call, I have to go and write on the stack and decrement the stack pointer and write in memory is a write, so maybe it's not so important because it will happen later. I have a load store queue, and the store queue will store later. But whenever I want to do a return that on top of that I'm not able to predict very well, I will have to go and read from memory. So compute something about the stack pointer, take it, read from memory, and use this address as my destination. And this will take a lot of time, right? And has to go into main memory. Okay, of course, I hope that my cache will hit, although there is no guarantee. My cache will hit so that I will be a bit faster. But still, I mean, I'm doing one of those instructions that are, in a sense, terrible because they are these memory instructions that have to go out and use something that is relatively slow. So why don't I do something better, which is to say, I take a little memory of some size, and I construct inside the processor, not outside, not in the main memory. This is my register, my buffer internal. And I do exactly the same thing that I was doing here by adding the return address here. And whenever I issue a return instruction, I take it out. It's exactly the same mechanism, except that I don't have all the other crap that the user decides to put on the stack in the middle. I have only the return address, which is what I'm concerned, and is essentially the same thing. So instead of going out into memory, computing addresses, updating stack pointers, and so on, I do it internally to my processor. Now, the clear idea that we want to have at this point is to say, this is a perfect predictor, right? I do these two things. If you really want me, because I cannot change the semantic of the instruction call and ret that has to manipulate the stack, and I have to manipulate the architectural state in exactly the same way because you're looking at me. Let me do this hidden, and I use this as a predictor, and it will be a predictor that, under some hypothesis at least, will be always correct, right? You keep putting here a second function and is a second return address. It will be here. I will pop them in exactly the same order. So there is no reason, almost, I'll come to that in a second, but there is almost no reason for this to be disaligned or desynchronized, right? So whatever I get here from this is a perfect predictor of what my return should do. So first of all, I have solved my problem, right? We wanted to have a predictor for this case that is terrible a priori, and now I have one. I maintain internally a mini stack that corresponds to the serious stack. I do still everything that I need to do on the serious stuff, and maybe eventually I'll always check that what I have from the mini stack is the same thing as the real stack, so that I'm sure that I didn't do mistakes. But I use the mini stack to go much faster because from this one is just a little buffer. So within a cycle, within a fraction of a cycle, I take out the correct value from this. Okay, so I solved the problem of prediction. So finally, I have a way, which is called return address stack, to predict this very special category of jumps that unfortunately are also very frequent, so are very bad and yet very frequent. So now I've solved them. Of course, there is a question that is natural at this point, is why did we invent at all this apparently stupid idea of putting the ret on the external, on the main memory stack? Why in the first place x86, MIPS, or whoever will not have a structure like this architecturally visible, so declared? This is the way a stack, a return address stack works, is this one, number 2, and not number 1. So number 1 is a bad idea because it has to go into the memory, main memory, so it's a mess, it's slow, and so on. Since we do calls and rets all the time, let's have a structure inside, and this is our solution. Great. Why not? Well, the problem is, the sort of usual problem for this kind of structures is that, okay, but this has a specific size, right? This is, say, the number, 16 entries. What can go wrong? The moment I'm calling recursively, not recursively actually, but sort of nesting the call of 16 functions. So in the 15th or 16th level, I call one more level of function, some other function. Well, here I have a problem, right? I have put here, I have my return 16, the last of the returns, and now where do I put return 17? Where do I go back? I don't have it. Now, I could throw an exception, stop everything, and so on, but the problem is I cannot build programs, at least not easily, where I have an unlimited number of nested functions. This is a classic example, and is the example that I was referring to before, is a classic type of example of situation that it practically will never appear, right? I will figure out, I have absolutely no idea, as Paolo Ienne, how many nested calls there are in a typical execution of Windows and programs in Windows and so on. But I can experimentally find out, and I figure out that there are, I'm saying a number at random, 128, almost never seen more, or never seen more than 128. I'll do this structure 128, and it's perfect. Well, it's not perfect, right? Because I must guarantee that if someone else comes and does a very, very strange program that does 129, it works. So there is no solution to have here a number and get away with it. Yet it may be very likely that I have a number there where maybe in the lifetime of my processor, it's never exceeded. But this is the difference between guaranteeing to be exact, to do the right thing, which I can't with a fixed number here, and being almost always, or always in practice, right. There is a fundamental difference. And this is, again, the strength of prediction, is that what I need to do in practice, in reality, is something that is universal, that will never fail, and there is no way to make it fail. But this thing is much more complicated, in the sense that I have to go to memory cache, figure out that is a miss, come back, and so on, is much more complicated than it needs to be in most of the situation. And so in most of the situations, I can use this internally, hidden from your knowledge, and get away with it by doing the simpler version. And only in those very special cases where my shortcut is wrong, I'll revert to the complete version. So this is a concrete example of what I was saying before. That is that sometimes, or in most of the cases, we have to do things extremely complicated because there are edge cases that might or might even not happen ever, but we need to take them into account and complexify our life. The beauty of prediction is that I can go ahead, and again, prediction and speculation, right? I take this and I take it for good. We'll figure out if I made a mistake, but I'll take it immediately. So I can get away with a simpler version that ignores the complexities of life. And if nothing happens, that was one of those strange situations where that was not the right thing to do, I've gone and I've been much faster. So again, this brings us to what I was saying before. Prediction and speculation bring us in a completely different world, where we forget about something and just go ahead. And that's what makes it powerful, right? It's just that we ignore things that are incredibly rare, but we cannot ignore if we want to have something semantically correct and sufficiently general, even if we know that it's most unlikely that it happens, but it's not zero probability, so we need to take care of it. Now, before abandoning this part on branch prediction, I want to give you a sense of how important this is, how it is, how bad it is to do 5%, for instance, of mispredictions. And it's going to be useful for much later, not much, but in 1 or 2 weeks, I think, because it will be a motivation for what we are going to do next. but it's in general important to understand, yeah, so is 95 a great prediction or not, or shall we try to do better? And essentially, the problem that we have is the one at the bottom, right? The probability that my prediction at a specific point in my code is correct is the product of the probability that not only this one is correct, but also the ones potentially speculated that are before are also correct. So you understand, I can predict on one direction at one branch, and before this branch is resolved, maybe I land on another branch and I predict also this one, and I continue following this prediction and I predict another one. And now the probability that what I execute is correct is only the probability that the first one is correct, and the second one is correct, and the third one is correct, right? So it's the product of all the prediction that I do at the same time. And given that we have these machines with sort of an incredible number of in-flight instruction at the same time, and in-flight instruction mean instructions that are, for instance, in the reorder buffer, are not yet committed and are at some point of the execution, whatever it is and whichever it is, with machines that have a large number of them, the probability that there are many predicted branches at the same time is relatively high. And so the formula that you see at the bottom, the fact that the probability that the next instruction after the last branch is the correct one to execute is the product of the correct prediction of all the previous branches, becomes extremely important. And so try to do something quantitative. Here is an example of the latest architecture by Apple. So just came out. Maybe some of you have already bought one of the Apple computers that has an ARM inside and is one version of this architecture. And one of the things that you see is that there is a ROB. I'll come back to this slide a little later, but you see here the ROB. We know exactly what it is, and it is pretty big, right? 630 entries in this ROB, which means that this architecture has somehow, maybe there are some mistakes that I'm doing in this discussion, but just to get orders of magnitude, there are essentially 630 instructions that are up to 630 instructions that can be in flight in this architecture. So it's a big number, right? And we can imagine that I think there are some statistics that someone tried to extract, but typically every, 15, 20 instructions, there is a branch, right? So try to do that, right? 630 divided by 20, let's be conservative. So 600 divided by 20 is what? Is 15, is it? No, 600 divided by 20 is 30. So 30 branches in this reorder buffer, there are 30 branches that potentially are all non-resolved yet. Now, go back to this formula, right? Assume that it is 95% the probability of predicting correctly, which seems reasonably high, right? Now, is the product 30 times of 0.95. So the probability that the 601 instruction in that reorder buffer is the right one to execute is 0.95 to the power of 30. So try to do that. I'll stop because you have to take out your calculator and do it by yourself. So you've done it. How much is it? It's terrible, right? It's something around 20% if I did the calculation correctly. Again, it's a completely wild calculation. I'm forgetting a lot of things, but the order of magnitude, right? The point is we are below just randomly choosing the outcome of a branch, just saying, okay, half the time I'll say taken, half the time I take not taken is 50%. it's 20%. So I'm even worse than that. So at this point, how interesting is to try to execute this 601th instruction? Pretty pointless, right? So this is just to give you a sense. We'll come back to the problem of, okay, so what do I do, right? We'll come back to this in a later course. What I want to say for now is that, okay, 95 looked very good. Looks, my God, I'm really good. Well, the perspective is that given the size of these machines and the kind of organization that we have, 95% is actually not very good, right? And you can do the same calculation with 99 and see if you are a bit happier, right? And certainly will be happier. I don't know how much happier. All right. Again, big zoom out. I hope you are not completely lost in what we are doing, right? We are looking at this idea of predicting a speculation. We have realized that I'm just trying to make a little summary so that we know, because of this zoom out, where we stand. We have realized at the beginning of this lecture that we have done already some prediction and speculation, and it was the precise exception. We have started looking into branches that seem to be an important area to try to predict and speculate, because they are a definitely important class of things that we have to wait for while we are executing, and that prevent us to extract parallelism, because we don't know where to go to get the code and search for parallelism. And we have looked at the fact that speculation is actually relatively easy, because it's essentially the same idea that I had for precise exceptions, for implementing precise exceptions. And prediction is what we have done until now to figure out that there are ways that are actually relatively sophisticated to get prediction, and prediction relatively accurate, whatever is our definition of accuracy that we need to meet. So again, we come back to the what's next. What is the next thing that we can predict and speculate upon to improve our performance? Well, at this point, it becomes a hunt for all those cases where we have something to wait that we don't want to wait for. And so we can go back, for instance, to this case, which is the case of dependencies through memory. Remember how our load store queue was working, right? And the kind of situation it could find itself on. And here is a little reminder simply from one of the slides that we had. If we have here a load at a specific address that has a bunch of stores that are preceding, and we don't know the addresses where some of these stores are going to write, we are unable to determine whether there is a dependency or not. If there is a dependency in one of these stores, it is one of these values that will be written in these stores that is actually the value that we want to return from this load. But if none of these two stores will have here a value when it will be calculated, right? We are waiting for them. As soon as they will be calculated, if it turns out that they are different from this address where I'm going to load, actually I should go and load the value from memory, and this value will be correct. So it's a perfect example where I'm waiting for something to tell me there is a mistake, but I could go and do the job now, and I have a good chance that it will be correct. So again, the prediction is extremely simple in this case. Is essentially what I just say, right? I can optimistically assume that there is no dependence. In general, code is the most likely situation. Of course, it depends on what the code represents, but it's a very common situation that there is no dependency. And I can use it to go and speculate. And the speculation is that I can go and read this value, which is the operation that I should normally do. And if I'm wrong, I simply take whatever I computed with this value and throw away. Now, I should not throw away whatever is after this load, but only what depends on the value that this load brought back, right? So maybe there is some other some other operation afterwards that has nothing to do with the value from this load, and this will be correct in any case. If I make my life easy and I decide that in case of misprediction, in the case where there was a dependency, I throw away everything, the load and everything that follows, even if independent, it makes my life easier because I can use the same mechanism for speculation that we have seen before. That is, I use the reorder buffer to throw away all the following instruction. Note that the only prediction that makes sense, not only because it is the most frequent case in almost any program that I can think of, but also because it's the only one that makes us gain time. So if I always assume that there is a dependency, this is actually a very bad assumption in the sense that I have to wait and I'll never be wrong. But I have to wait. So I even have to wait when I will not have to wait. So basically, it's only a damage. So this is the only thing that makes sense is to do what I described. So on the speculation side, there is not much to add, right? If I squash conservatively everything that follows a load, a load of which I predicted no dependence, it's easy. It's the same game that we have played until now. I will have to change a little bit my reorder buffer, but I think you understand perfectly well how, because it's essentially the same idea that we have implemented a couple of times already. From the side of the prediction, what we said is the only static prediction that makes sense is to say there is no dependency. Now, I am repeating what I said before, but I added the word static in the sense that this is a prediction that is true independent from the history of a specific load. Now, this problem of figuring out if there is a collision between two addresses through memory will come back a number of times in this course, in different forms, in different contexts. And it is an important one, right? Because it is one of those things, dependencies are one of those things that, real dependencies, sorry, just to be clear, real dependencies are one of those things that intrinsically delay our computation because we need to wait for some value to be able to continue. So it is an important source of delay that we need to honor if there is really a dependency. And memory is one of the places where we often don't know if there is an actual dependence, right? Everybody sees that between two instructions, one writes in R3 and the other reads R3, there is a dependency, so it's very easy. Memory is not, right? So it's actually one performance issue all over the place, and again, in very different contexts. And one of the problems is that sometimes there are dependencies in memory. So it depends very much on the program that you are looking at. In some cases, there may be never a dependency, and you can see this prediction as yet another case of what we were saying before, right? Out of pure conservatism, I need to assume that maybe there is a dependency. And then, like in the slide that we had here, I need to wait. In other cases, maybe there are actually dependencies, but if there are never, I have to be conservative and I spend a huge amount of time, whereas I could go ahead and win. So once more, it is one of those areas where prediction and speculation is great. But in the case that there actually are sometimes some collisions, and so I make a wrong prediction by assuming that there is no dependency, maybe the cost of replaying everything that is after the load is very high. So again, look at our idea of processor with our idea of reorder buffer. it seems to cost nothing to replay because you just immediately zero everything that is in the reorder buffer. Now go back, for instance, at what by now I think you have seen and you know of the R10000, and there you have to go and empty the reorder buffer in reverse order to squash. So you spend cycles to squash instructions. And again, the R10000 is actually a much more realistic version of the qualitative processor that I tend to show you in the course. So there is a cost of making a mistake. And so one could try to do better prediction than the simple static dependence prediction. Now, it's not difficult to imagine what to do, because you can do something that is similar in spirit to the branch predictors, right? Something that remembers the PC of the load and uses this to remember whether last time this load had a conflict with a previous store, and maybe even with which one it had a conflict, or if it didn't have any conflict. And based on the hypothesis that, again, is not a certainty, but is something that happens very often in our programs, that there is some stability, that is, there are some dependencies that come more often than others. This would help, and would help in two possible levels of prediction and speculation. It could predict more accurately whether something is independent, and I can simply go and execute, hoping that I'm right, or it could tell me, oh, there is a probable dependence from that store, so that I can tentatively go and do a bypass through that. For instance, imagine in this case, if I have a predictor that tells me typically this guy is dependent, or last time that I've seen it, it was dependent from the store to store previews. So this one here, I could, even if I don't know where this guy is storing, I know where I'm loading, but I don't know where this guy is storing, what I can do is still take this value and say, okay, maybe this is the value to use because that was the case last time that I've seen this load, right? And so this is a further level of prediction and speculation, because I don't only predict that there is a dependency, but I always predict with whom I'm going to alias, and this may allow me to go even faster, because then I can not wait even for the store to be in case of dependency, but short circuit even then, and take a value faster. So we are back to our list, right? So we added very quickly, because there is not so much to add qualitatively, because it is a very simple prediction, or some predictions that are not qualitatively different from the ones that we were doing for branches, and from the speculation perspective is exactly the same mechanism that we have studied. So very quickly we added one extremely important element to our list of possibilities of prediction and speculation. And once more, we can ask ourselves, are there other things that we can predict and speculate upon? In our hunt for all the things that keep us waiting, clearly caches and misses are one of the hunts. Caches are there to reduce the memory latency, in the sense that they help us get an average time to access memory that is way less than without it. And out of order execution is there to partially hide this latency by deciding that, well, let's do something else while this data is coming back from memory. The problem is that in some cases and in some contexts, we still may have a significant number of misses. Many of them may be compulsory misses. I think you I hope you remember the sort of classic classifications of misses, where there are capacity misses in the sense that you don't know, you don't have enough space to keep all the data that are common in your program. Associativity misses in the sense that for what we discussed before when we were talking of aliasing between branches, you don't have enough places to keep elements that are that have some part of the address common, so you have to throw away one because there are not enough places to put that particular element of data. So it's not the complete capacity of the cache that is a problem, but is where you can put a piece of data that is a problem. So these are parameters that you can control, and you can do better, more expensive caches that maybe are solved. But then there are the compulsory misses, that is stuff that you have never seen, and that there is no other way than to go and get from memory. And for all of these things, including the last one that is the most dramatic in a sense, there is one idea that could work, which is to say, well, if I can guess what will be asked of me later, I can go and fetch it before it's asked. So when it is asked, it will be in the cache. Now, the interesting part, if you understand what I just said, maybe I was not totally clear, is that I go and I get it and I put it in the cache. So the speculation of is in this case extremely simple. We are putting the data directly in the cache, which is not architecturally visible, is only my business. And if I made a mistake and I put something in the cache that I should not have put, it's not a problem. At least it's not a functional problem, in the sense that I will try to look for what I actually need, is not there, and I'll go out to memory and I'll get it. So it's one good part of this prediction and speculation, is that the speculation is actually almost inexistent. It doesn't mean that it doesn't have a cost, because it means that if I brought in something wrong, I will have polluted. I will have thrown out something that was in the cache, and maybe it was something useful. Maybe I brought in something that is totally useless, and I throw away something that later will be useful. Therefore, the overall effect of this speculation, of this peculiar form of speculation, is actually damaging. So the place where one does places this mechanism of predicting the next prefetching, that is predicting the next miss, is actually very different from all the other predictors that we have seen, because it's not something that belongs to the core, is more something that belongs to the cache. It may be useful in some cases, people do, to connect this prefetcher also with the core, in the sense that the core may have side information about the access that may be useful for the prefetcher to make a particularly good prediction. Maybe the most trivial thing is, if I'm here, sitting here, I know only that this is the address that I'm asked, and maybe I want to guess what is the next address. But if I have information from the core, I may know that this is the address that is asked, and is asked from a load that is at a specific address in the program. So I could distinguish who is asking for what. That the core has this information, because as the PC, if I'm sitting alone there, I just see what is asked, but I have no idea who asked it. So there may be some connection with the core, but again, the speculation itself has nothing to do with the core. The core is completely independent from this speculation. And this is in contrast with the three techniques that we have seen before. In the three techniques that we have seen before, we had to do let's say, massive changes to our processor, that is, add this reorder buffer. Once we have done it, it was good also for the other two, but initially we had to do this massive change to the pipeline to have this reorder buffer. Here, the core doesn't need to know anything. In fact, it will know nothing. It will just ask something, and oh my God, I found it in the cache. That's it, right? Or I didn't find it. I'll wait. So there is absolutely no modification in the core in this case. You also see that the prefetcher can be at the output or close to the output of different levels of cache, right? The cache of level 1 can try to predict what you'll ask of it next, and what could be the next miss that I will have in L1, but L2 can do the same, L3 could potentially do the same. Clearly, the lower I go, the more difficult it is to make sensible predictions, right? Because if I am at the top, if I'm at the level of the core, I see every access, and seeing every access, I can imagine if there is some sense of a specific sequence, I see all the element of the sequence, it's easier to guess what is the next. The more I go down, the least I see of this sequence, because I see only the misses of the previous levels. So guessing and understanding and making hypotheses about what is the sequence that I'm seeing so that I can get the next element of the sequence becomes more challenging. So typically, they are only at the highest level or higher levels of the cache hierarchy, and the mechanism used at the different levels may be different. The strategies may be different. Now, what to predict and when I predict some miss, right? There is the two parameters are extremely important, right? The what is self-evident. I need to know what is the next miss and what I should bring in. But the one is also important, right? For instance, if I predict too late, and we'll see a potential example a little later, if I predict too late what I have to bring in, I may not gain much, because if I'm starting now and I need 100 cycles to bring it in, and I will be asked the next cycle, well, there are still 99 cycles to do, so it's not timely, it's useless, or is much less useful. Same thing at the on the contrary, right? If I ask it too early, right, maybe I am doing damage because I'm taking away from the cache, I'm evicting from the cache something that in the short term is useful, just to have something that is correct but sits there for a long time, or maybe it will be evicted itself by the time I really need, because something else will come in the cache and I'm predicting it way too early. How do I do the prediction is the usual game, right? I'll try to use typical behaviors that I know from a priori, from the fact that I do programs that have sequences of instructions. So typically, but not always, I will want the next pieces of memory that follow the current instruction, or I will try to learn dynamically from execution. And we'll see a couple of examples of each of these. Typically, prefetching is characterized by these two metrics. One is coverage, how many misses my prefetching manages to remove. So how good I am to guess the next stuff. And the other is accuracy, which goes very much with the risk of polluting. How many of the things that I bring in are really useful compared to the ones that I bring in and are useless, and therefore will only end up on pollution. Now, you clearly see that it is a sort of a trade-off between the two, right? Because if I go extremely aggressively and I have a great coverage because I bring in everything, so finally I will manage to bring in to remove the misses. I remove the accuracy because I bring in I bring in a lot of crap, and I will certainly end up polluting my cache. If at the same time I try to be extremely accurate and I bring in only those things that I have very high confidence that will be useful, I may be good at being accurate, but then my coverage is small and the benefit that I get is particularly bad. So all the techniques try to find some sort of balance between these two metrics. And what is the simplest prefetcher that you can do? But the simplest intuition is the one that I mentioned already, is that in many cases, if you are in the instruction cache, for instance, you have a sequence of instructions that often you continue executing. If there is no branch, you continue executing. So if you are bringing in a line of the cache, maybe it's a good idea to take in also the following line, right? Because there is some chance that you will use it. The same is true on the data. If you are exploring an array an array and going through the data of an array, you have essentially the same thing. Notice that these are compulsory misses, right? There is no way, unless I prefetch it, when I take this instruction cache, right, line, if I have a certain cache line with multiple words to exploit already the same phenomena, that is spatial locality, the fact that I tend to be in the same area executing, and I execute this, so I removed by the cache, and by this long line, I removed a miss here, a miss here, a miss here, and so on, but I cannot remove a miss for this next word that is there. So if I need it and I prefetch it, I suppress in principle, one of these tough misses that are the compulsory misses. The way people tend to implement this, which is relatively easy to do, is maybe not to literally do what is said in the second line of the slide. If the X is a miss, don't load only X, but load also the next one, is to do essentially this, but do it at a different timing, or wait for a confirmation that is going to be really needed by continuing letting the processor do a number of accesses maybe in this cache line, but only when it is close to some distance from the end of the cache line, so within some bound from the end of the cache line, saying, okay, but then we are really getting to the end, so bring in the next one. So the idea is that if there is a branch here, I will never fetch anything here, and therefore I will never bring in the X plus 1. Now you understand that this has all to do with the also with the timeliness, right? If I do the fetch ahead, or by the time that I am within the fetch ahead distance and I'm here fetching this one, maybe it's too late to bring in X plus 1 because it will take too much time, right? If I'm here fetching this one, maybe I'm fetching, because I'm a superscalar, I'm fetching these two at the same time. In one cycle, I'll be fetching something that is outside this boundary, and in one cycle, it will be too late if I haven't brought it in already. And so if it was a miss that I'm anticipating, probably I didn't gain much by starting it only one cycle before. One thing that I want to remark, and I already sort of, by the way I was explaining, I think it was clear, it is the same game that we are doing in terms of bringing in these values, so the x+1 cache line, when the cache line x is being requested, is essentially the same game that we have played already with the cache line length when we brought in this word the moment we were asked this one, or if I am faithful to this picture, the fetched instruction is this one, and we brought in the one after and actually many after. So in some sense, the fact that we use caches with longer cache lines, and I hope again that everybody is clear on how we build caches and why we build them the way we do, we always use cache lines that are longer than a single word, or even worse, a single byte. The reason of this is that this is the only mechanism that we have to exploit spatial locality. And what we do here with prefetching is also that we are trying to exploit spatial locality. So one could also say, but since the two mechanisms do the same, why do you invent a second method, the next line prefetching, to solve the problem now? Why don't you do your cache lines much longer? Why don't you take a cache line that is 4 times longer, and then probably I'll reduce the number of compulsory misses by a factor 4, because now the cache, the miss will not be every, let's say, 8 words, but it will be every 32 words. So again, 1/4. So you can imagine yourself why prefetcher mixing a bit of long cache lines, but only to a reasonable extent, and then going to a prefetcher works better. One of the intuitions could be that there is a more finer grain control or a segmentation of the data. In one case, if you had the huge, ridiculously long cache lines, you would probably manage to reduce in some specific cases many of the compulsory misses, but in many other situations you will just pollute the cache by bringing in, just because you need only one word here, you bring in a huge amount of other data that are potentially completely useless. In the case of prefetching, you bring in a slightly bigger quantity than what is needed, but only when you see that there is a need of something more, you bring in something more. So it seems to be more adaptable to different situations, and not a solution that is great for something but may bring a damage in every other situation. One other version or extension, which is a natural extension of the next line prefetcher, is the next n line prefetcher. That goes back to what I mentioned a few seconds ago, the fact that when you are in the fetch ahead distance and you decide that you want to bring in the next one, may be a little too late, right? It depends very much on the context and on the situation of your processor and what you're doing exactly. But you may realize that you have to bring in something a little too too late. So the idea will be that you use maybe a similar mechanism of confirmation that you really want this, or that you really have these sequential accesses, but you don't prefetch only x+1, but also x+2, x+3, and etc. until n, and that's what next n line prefetching means, and the next 3 or the next 5 lines, and so on. And of course, n is the trade-off between these two elements, coverage and accuracy, because if you make it too small, maybe you don't have coverage because it arrives too late. You haven't yet prefetched what you immediately need. If you make it too large, you have poor accuracy because maybe you'll never get there, so you fetched something that is not particularly useful or not useful at all. Another dimension that you can add to this is the one of stride. Stride being the step, right, between two elements of a sequence. And we have looked at now at a sequence where the distance between the element of the sequence, at least in terms of cache lines, is 1. So it's one cache line and the next and the next and the next. There are other pretty typical cases where what you are doing is not accessing, is equally regular in a sense, but the distance between accesses is not 1, but is something else. For instance, when you're accessing a matrix in a C sense, right? C, C++ will store the matrix column-wise, right? You don't care about anything else on the side, so you don't care of anything here and anything here, but to go to the next element, you have to move to an address that is maybe 1,000 or 10,000 elements away, depends on how big is the matrix, right? The same applies if you are going through one element, a specific field of an array of records, right? I call it struct if we're speaking C. If you're going through this field to search, for instance, if one of these fields is my name, you don't care of anything else, but you have to increment every time by an amount that is the size of this structure that can be potentially very large. So it's a natural extension of what we were doing before, is to have a stride prefetcher that is on a request for X, I will prefetch the cache line that is S cache lines away, or for an address A, an address that is an address A plus S, whatever is the corresponding cache line. How do we do this? Just to give you a sense, this is very pretty abstract, but a sense of the circuit that can do that and the sequence that one can try to do it, is that it takes a little bit of time, maybe to a bit of elements of this sequence to confirm that we see a sequence, and when we are confirmed, we start generating prefetches. So for instance, imagine that I get an X, it's a compulsory miss. I cannot do anything, it's a compulsory miss. I get an X plus S, it's still a compulsory miss. I can go and search, but I can start subtracting these two accesses and saying, okay, I have an hypothesis of stride, right? I now have a stride that I can put here, and I can say, okay, maybe my accesses are all S away. And when you see another addresses, right, the X plus 2, you see from the previous one, and you add, so this was X plus 2, you add S, you have X plus 3, you have X plus 3 that comes, it's equal, you confirm your hypothesis, but you still haven't predicted anything. You are counting a number of matches, and you go on for a little bit until you have some confidence that what happens is that you are always getting a request that is equal to the one you would have predicted with this stride. And so when this number is sufficiently large, in this example I think is 2, I have 2 confirmation, you start to say, I have a guess. The guess is the current address plus the stride, right? So it's a circuit like this that you are trying to basically use in different ways. There are a number of problems that still need to be maybe solved. Is exactly where do you start, right? You don't have only these accesses from the memory, but you have plenty of others. So how do you try not to mix different sequences as if they were from the same belonging to the same sequence? how do you handle that? One thing I suggested before, maybe the core can tell me which load had this compulsory miss, so that if there is another load that is completely different that has a compulsory miss, I don't think it is the same sequence. I think it's actually something totally else, and I don't pollute my guess and my predictor that I have here, my prefetcher that I have here. One idea that is a little orthogonal to this and is actually a useful idea at the moment, I tend to have many of these prefetchers that sort of mix their accesses, and also the fact that if I am too aggressive, I'm going to pollute the cache, is to create some storage that is specific to these prefetchers and create what are typically called stream buffers. So I have a FIFO where I keep these things that I'm prefetching. So I have some type of prefetcher, typically some either next-10 in line or some stream prefetchers, and some storage. And I keep prefetching, bringing in from memory and just putting it in the FIFO, as opposed, as I was doing until a minute ago, bringing whatever I prefetch, putting it into the cache. And what is the idea? The idea is that I'm not polluting the cache. Of course, I'm adding some storage, so there is a downside to it. So it's not perfect comparing to put in the cache. But the advantage is that I'm not polluting the cache. The cache has always its policy about what is important and what is not, and maybe is a very good policy. I can have many of these FIFOs for different streams and different types of predictions. And when the cache has a miss, instead of immediately going down and saying, okay, memory or next level of cache, give me the data, the first thing that it does is to look into these the heads of these FIFOs to see if one of these is actually the right value. And if it is the right value, of course, there is a very quick miss, in the sense that immediately I bring it in and I found my value. And if I don't find it anywhere here, I have essentially one of two possibilities. I maybe think that has nothing to do with the streams that I have that are sufficiently successful, and therefore I just simply ask from lower level memory, or I take one of my stream prefetcher, the least successful that I have. If I have some counter that tells me how good they have been, I kill it and I replace and I try to build a new stream based on this miss, hoping that it will become successful at some point in the future. So we're back again to our recurring slide, right? And we have added one very important element to this prediction and speculation. It is a different type of situation. I remind you of what we said. The first three depend on the core doing something microarchitectural that should not be shown architecturally, and therefore have to some complexity in the processor to hide what is actually happening in the processor from what the perception of a user looking at memory can be. This is very different because actually we are playing around with something that is not architecturally visible, that is the cache, and so is actually a different game somehow, but still depends on this idea of going and making prediction and doing things ahead of the time that they need to be done. This is an area that is actually also pretty active research, and prefetchers are in all our cores these days. It's very important because caches become, in some sense, less and less useful, or at least it depends from the applications, but there are more and more maybe applications where caches become less and less useful. think of that, right? That the idea is that in a cache, I keep all the data that I'm operating on. If I'm doing things like, I don't know, an FFT, I have a few thousands of values maybe that I care, that I keep operating for quite a while before I have computed my result. And so a cache works superbly well for this, right? On the other hand, if I'm taking a graph with 1 billion edges and I'm trying to search for, I don't know, clicks inside this graph, caches are particularly useless, right? Because I am almost guaranteed that my graph will not fit in the cache. I'm going to explore different parts of the graph sequentially, right? So I will reuse very little the same edges, because once I've seen and I'm visited, I don't care anymore, probably. Depends on the algorithm, of course. But I have this gigantic footprint of data, and I will have a huge amount of compulsory misses. They don't have to do much with my capacity, or at least with my capacity in a reasonable size of cache. They have nothing to do with associativity. So there is not much that I can do on the cache to solve the problem. The only thing that I can do is essentially prefetching, that is guessing what is the next edge that I want to read and bring it in. So people are doing very sophisticated things in terms of prefetching, way beyond what I shown in the previous slide. But I don't think it is important here to look at them. I must say also that people have been looking into the idea of using some other cores, since the problem is the cache, and if finding in the cache, I could use two cores that use on the same cache, one to use the real cache and do the real computation, and another core that only issues request to the cache, so that forces the cache to realize that something is amiss and bring it in and essentially prefetch data for the other core, right? Which is a completely software solution to this problem, right? So it's a big area. Come back to us. What's next? What can we do now? In fact, not too much, right? When people understood that this game was very useful, and especially when people realized that the reorder buffer would help to basically speculate on whatever you want inside the core, people have been playing with a number of things. You could imagine that, I don't know, some source operand of some instruction is a sort of always the same. It does happen, right? If you look at some of the programs that you write, maybe you can think of functions. Do you call the functions or a specific function with one of the parameters that is always the same? Maybe sometimes yes, perfectly yes, in the sense that is actually the only, in practice, you never call, and you know, one function that you wrote with any other value than a specific constant value. So one could try to exploit some of these things even dynamically inside the processor, or can understand that maybe one value in some calculation has a fixed stride, right? In the same spirit of what we have just seen for a prefetcher, that the sequence is a sequence of elements at the same, each at the same distance from the previous one. None of these techniques have been terribly successful. I'll show in a few weeks, actually in some weeks, some example of value prediction. It's open, right? It's none of these ideas that people had seem to be particularly useful. But depending on the system that you are building, and especially if tomorrow you find yourself to architect something that is maybe an accelerator for something in an FPGA, which is not a processor but is a processing element for some specific situation, maybe in that specific situation there are other values or strategies that you can apply for to the same extent. But before consider this this chapter closed, there is another broad area of another space of application of this concept that I think it's important to survey. We'll come back in many cases to this later in the course, but I think it needs to be mentioned from now. From now, we are looking at this. We have looked everything that we have done today and last week has been essentially and exclusively for dynamic, right? In the sense that we leave the binary code totally unmodified, there is no change in the program, but behind the scene, behind the visibility from the programmer, we do strange stuff and make this hypothesis, and we come back if we made a mistake, and so on and so forth. There is another possibility, which is in principle equally interesting, and which belongs to this static compiler-centric world that we'll start exploring in I don't know how many weeks, I think in maybe 2-3 weeks. This idea that I can change the code also to do this, also to let's try to do this in the case it works, and maybe come back and do something else in case it turns out that I was wrong. And it's the same, completely the same idea about the prediction and speculation, but it's done in a completely different way, because it's now is the compiler that tries to do this, or if you want, the programmer that makes some reasoning about what is happening in this in the program and decides to do some changes. So here we take a program and we change it. And let's take this this example as a way of thinking about the problem, right? So let's look at the example. I wrote it also in C, so that is a bit easier to read and to understand. So I'm making a comparison, and then I make 2 different assignments to A, depending on the current value of A. So let's read it later. I don't even know what this assembly language is meant to be, but I think everybody understands, right? It's some sort of, maybe it's also correct MIPS, but not completely correct, but it doesn't matter, right? We all understand what it does. It does a load of one address, which corresponds to A. Now A is in R1. It compares, it checks if it is not equal to 0, R1, and if it is not equal, it jumps to the else clause. That is, it adds to R1 4, keeping it in R1, and then it stores this in the same address. You see it here, in the same address where I took this value, I put the new value that is 4 units bigger. And if this test failed, that is, if we are in the then, I do a load of something else, which is the B, and I jump in this L2, which saves this something else that I put in R1, it saved in the other location, which was A, so I save basically B in A. So I hope everybody is absolutely clear in this piece of code. Now, assume that I have some easy prediction that I can make because I know this code, because I know what it does, and so on. And I do know that the then clause, that is the A equal to B, is almost always executed. So it's by far the most likely of the two possibilities. Now, what can I do to improve this code? And again, I hope you are clear about the name of the game, right? It's again prediction and sort of speculation. We'll see in which sense it's really speculation. But the way we are changing it is now we are just playing the compiler game or the programmer game, right? We just want to do something in this code so that it will execute better. So this is the world of static optimizations of things that we do before execution, fairly different from what you have done so far, which is I change my hardware so that you give me the same program and I'll execute it better. I'll do a break so that you can really think of it, but I want you to think of two things in this break. Not only what you will do to improve the speed, the speed of execution of this piece of code in reasonable assumptions about what may happen, but also why you cannot do what you would like to do. So there is one thing that is, I think, the most natural way of exploiting the condition that we have here, but unfortunately, we cannot do, and I want you to think why we cannot do it, because maybe that is actually the most or the least evident part of this optimization. Hopefully is clear to you what we would like to change in this program to optimize it. And I hope it is also clear why we cannot do it. What we could do to improve is that the loads are the classic instructions that may take many cycles, essentially because they could be misses. So we would like to bring them as early as possible, right? Do them as early as possible. Now, qualitatively, LW, the first LW that is here, the read register 1, or sorry, the address R3, is no problem, right? I have a number of instructions here, all those that are independent from this one in terms of write after write, or not independent from R3. I just can write it as early as possible. In some sense, the same is true of the second load that I want to anticipate as much as possible, but there is a little bit more problem because here there is a branch. So this load is not guaranteed to take place. So I need to be careful and play around with my register renaming, do some register renaming in such a way that everything comes out well. And let me do it interactively for you so that we try to reason about it. And once we have done it, we'll also ask ourselves why we actually cannot do this. Okay, here is our code again. And once more, my purpose is especially this load to send it to start it as early as possible. So what I have a problem, of course, is that there is an R1 here and an R1 here. So if I just move it around, I have a write after write dependency that is going to create trouble. So clearly I need to rename this R1 into something else. So what I can do is, in whichever order I want, to have the first load word that loads in R1, 0, and R3, and the second load word that I rename the destination to something that I'm not using. For instance, I think R5, 0, and R2. And these two instructions can go as early as possible, thanks to, as soon as there are no issues of dependencies. And then I change maybe my code slightly here. Let me think what I want to do. I want to end up in the same write. So I want to write in 0 R3. And what am I going to do? R5 is the one that is not modified. So maybe I put here R5. And here I do a test, which is the opposite one. So branch equal to 0. If it is the correct syntax, I don't know, but it doesn't matter. And if R1 is equal to 0, I go to L3 which is this instruction. And if not, I add my 4 to A, which is R1, but I put it in R5. And let's look at this if I am semantically correct, if I kept the same meaning. So I have in R1, I have A, in R5, I have B. If A is equal to 0, then I jump, so I write in A the value that I took from B. If A is not equal to 0, I take A, I add 4, and I put it into the location of A. So I hope it's clear that the two programs are semantically equivalent, and I hope it is also clear that I have a great performance advantage in the fact that now, except for dependencies that I don't know from the previous part of the code, that may be R2, the generation or the of R2, R3, I can anticipate as much as I want these two load words and try to hide the potential misses that I have. So exactly the same, qualitatively exactly the same thing that I have done dynamically until now, I can try to do statically, that is just by modifying the code. So this is the first thing that actually we can say, right? A couple of slides ago, there was a slide that was saying prediction and speculations are not an exclusivity of the dynamic world. It's something that you can do also statically. The question is, I cannot do that. This is wrong. For as much as the semantic seems to be preserved, this doesn't work. If my compiler does this, it's a disaster. And why is that? Now, I always sort of say a joke in this course. I'm not sure that I told you already, and maybe it doesn't apply too much to you since we are not interactive, so when I ask questions, you cannot answer, and we don't have an oral exam at the end, which is usually the case. But what I tell you is the following, right? If I very often ask questions, why, right? Even in the exam, right? I say, why this is happening? And if you are completely clueless and you are in the exam and panicking, typically a good guess is to answer when I'm asking what is the problem that we are going to have here, a good guess will be exceptions. Exceptions are sort of creating problems all over the place. Most of our performance issues for which we have a nice solution bump against the wall because of exceptions. And it is the right answer also here. The problems are exceptions. Why the problems are exceptions? Well, the problems are exceptions because I am anticipating, I am doing before I am allowed to this instruction, right? This instruction, in some cases, when I am incrementing A, should not be executed. Now, it's fine, right? Semantically, I'm not using the value, so where is the problem? Well, the problem is that maybe this instruction creates an exception. Now, there are different cases, right? There is a relatively benevolent, easy case where it's just a TLB miss. So this TLB miss has to be served. There's an exception. I have to stop everything. I have to go and reload the page and so on. I lose a few thousand cycles to get back there. But finally, it's still not wrong, right? It's just that I tried to do this to gain 20 cycles and I lost 1,000, at least in some cases. If it is sufficiently rare, maybe it's not too much of a worry. But something much, much nastier could be happening, right? It may be that this pointer, this R2, doesn't point to anything meaningful in case A is not 0, in case I need to increment it, right? You don't know, I don't know, right? It's a problem of the programmer. The programmer may have in B something that is in this pointer R2, something that is completely unavailable. And it's perfectly correct because the programmer has put a test and said, if A is equal to 0, do something else. Don't read B. So now you understand what is happening, and maybe this is a contrived example, but the general example is perfectly true, is perfectly applicable too, is I'm reading somewhere that I was not supposed to read. It may be an invalid address that it doesn't belong to me, it's a 0, it's a null pointer, it's something completely bad. The operating system sees that, says this guy is doing something weird, and is closing down my program. Now I have an initial program that is perfectly legitimate. I made a performance optimization that looks like semantically perfectly fine, and yet this program may stop and die, killed by the operating system for reasons that are completely outside the programmer control. So it's very difficult to do compilers, right? Because there are optimizations that look perfectly safe like this one, and in fact are a disaster. So what do we do? Well, in some cases, like this one, if we want to do speculation prediction, exploit some static prediction that we have. Someone has told us that very typically the frequent one of the two clauses of this if is taken more frequently than the other, and we want to do speculation by just optimizing the problem. In this case, we need some support from the hardware. And what we need is that we need a special way of performing a load that is not going to raise an exception. So we have this notion of poison bit, poison as in killing people, right? Sort of in knowing that there is something wrong happening here. So one additional bit in each register, and a special instruction that is this for example, this load word star, that is a speculative load, so that it does the load. It might realize that there is an exception, but it doesn't raise the exception. It just adds in this additional bit of R14, the poison bit of R14, a 1, a special marker, that is ignored until someone goes and read the value. And only at the moment I am going to read from a value, I look at the poison bit, and if the poison bit is 1, I report the exception. So what happens now? I'm doing this load. If it was okay to do it and it was the good speculation, I'm just reading R14, there is no exception, everything goes well, I take the R14 and I save it, everybody's happy. Now let's go into the bad situation. I am doing abusively, speculatively this load, and it results in an exception because I should not have done. So there is a 1 that has been put here. As soon as I go to incrementing A, because this was the right thing to do, I overwrite R14 with a value that is non-speculative. So this operation resets the R14 with A plus 4 and no poison. When I arrive here, I read R14, there is no poison, everything goes well, nobody will ever know that I tried to load something, I could not load it, and I generate an exception that was not shown to anybody. Okay, so this is a mechanism that we will see in a few weeks when we speak of one of these statically scheduled processors, and there will be a mechanism that is essentially very similar to this one, or it's a different implementation of this one, because maybe if you think about how to implement this, it's a little bit annoying, because every time that you read something, you have to figure out if you have to report an exception. So now you are, okay, in this case, you are doing a store, but suppose it is a completely neutral instruction, you have to figure out that you have to report an exception, but now you have to tell that the exception PC was this instruction, but you don't have this information anymore. So it's a little bit, it's beautiful to see on a slide, but actually if you were to implement this literally as it is said here, it's going to be a bit tricky, not impossible, but tricky to implement. And here we'll see that there is a way to implement the same idea in a reasonable way. And Itanium, which was a processor, we'll discuss about this processor, but was a processor that Intel introduced at some point, and then now it's completely dead. But in this processor introduced this speculative load, and actually a second type of speculative load that is actually, I think, called anticipated load or advanced load, sorry. Which is for another case of similar static speculation that we may want to do. Before I close, we are really getting close to the end now. Before I close, I want to mention predicated execution, another form of prediction, or maybe better, of giving up the ability of doing a prediction, a sound prediction, but definitely of speculative execution. It is, the name is predicated execution, or guarded execution, some people call it, and is a special form of speculating control flow, speculating a branch that I don't know where it goes. And instead of trying to guess where to go, I decide to do both at the same time. So I do both what is in the then side and what is in the else side, and basically commit to the registers, to the final registers, only the part that was actually correct. I'm not even showing now what this is exactly, because we'll come to it when we will do statically scheduled processors. It's a trade-off, because I end up doing more work, right? Now I'm not systematically, right? I'm not only trying to do the right one and trying to guess which one is the right one. Now I do both. But if I have a processor that has a lot of possibility of parallelism, maybe doing both things doesn't cost too much, because I have units that are not used anyway, because of the, maybe just because of these control dependencies, that I don't know exactly what to do next. So I don't know what to put in my functional units. Maybe I can put both sides of the if then else, and I don't do actually more work. I do more work, but I don't lose more time to do the work of both the then and else. And in the end, I find out what is the result, and I commit only that one. We'll see what it is. It's again a technique that is typical of statically scheduled processors that we will see a little later in this course, but is also actually also used in standard, typical, for instance, RISC processors. ARM has an instruction set that is in a specific way, but it is predicated. So it has this idea, and it exploits this idea. So this is a bit the summary of what we have and we haven't yet seen in terms of prediction and speculation. We have seen a few things for dynamic speculation, that is where the hardware takes this initiative of guessing and going ahead. I'm putting here something that is maybe a little funny, but and that people would not call it speculation, but is a form of prediction and speculation, which is virtual memory. What do we do? If there is a load, we send the load to the memory and it will go through the TLB. And it may turn out that actually the data is not available because maybe my page is on the disk. And this speculative load, in the sense that I started to doing it without checking that it is possible to do it, will come back with an exception that will say, hey, come on, the TLB is missed, and the operating system will come in the picture, refill the TLB, and will try to do this load again, and this time it will work after reloading the TLB and reloading the page from disk. It's a form of speculative execution that we use all the time, and we probably never called it so, but we make a prediction that every load is possible if it is legal, and we speculatively execute, and if something goes wrong, we solve it with this method of exceptions and system software. So it's also a prediction and speculation, and some of the others that are here are exactly some of the problems that we have looked at today. We have started started talking of some of the things that one can do on the static world. We'll come back to some of these when we will talk of this class of processors, and we have I have mentioned the possibility of doing some data value speculation, and there are some examples in the static world of data value speculation that actually turn out to be useful and exploitable. We will see this not so much when we'll talk of static processors, but when we will talk of dynamic binary translation. Maybe before closing down, it's a good time to attract your attention to 4 slides that I ignored last week, and maybe this is a good time to look at them. I don't have a huge lot to say about the slides, except sort of, again, bringing your attention to them, and maybe doing some relatively superficial observation. Then I let you look into them more carefully. I think they are interesting. The few slides are about recent and contemporary architectures, both in the Intel and the AMD world, because I think you can see, although not everything is clear and explainable in these simple figures, but you see some of the things that we know, right? For instance, here into the Nehalem, one of the recent architectures by Intel, you see a reorder buffer of 128 entry, and in the corresponding architecture from AMD, a 72 entry reorder buffer. You see here reservation stations, exactly the one that we described. You see that they are different in the sense that they are a single set of reservation station for all the different units. What else can you see? You see a memory ordering buffer that must be essentially a load store queue, so somehow correlated with the reorder buffer that goes in the register file. You have here the register file, by the way, where the reorder buffer writes. What else can you see here? Here you see explicitly some load store unit, which are essentially the queues that we also have seen. One particularity that is worth maybe looking at in these two diagrams is the complexity of the decoder that is very typical of the of the Intel or x86 processors. x86 is a CISC, is a processor that has a complex instruction set, and is one of those processors that people gave for dead essentially in the 90s by saying, oh, come on, they will never manage to do the same thing that you can do with these fantastic pipelines in MIPS processors. And what has changed is the ability of saying, I fetch and decode these say horrible CISC instructions, and I have these decoders that in parallel do in sense rewrite the program from this CISC language into some micro operations. Many instructions that we hope you use the most frequently will just translate into one of these micro operations, or maybe are already sort of RISC-ish instructions that come from the instruction queue. But if there is something more complicated, there are a complex decoder that can feed 4 instructions at a time and can generate almost a micro program, a small program that implements all the functionality of the complex instruction that x86 has. So I think I was mentioning in some other context, maybe a couple of weeks ago, the fact that you may have instructions that read from memory, do an operation, and write from memory in the single instruction, in the same instruction. Well, they are instructions that will be handled by this complex decoder that will generate maybe 3 or 4 micro operation that essentially corresponds to a load, to an operation, and maybe a store, and maybe some address calculation or post increment or something like this, right? So this is the orange part is an incredibly complicated part of these processors, and is is the key of, say, survival of Intel to RISC, and all the RISCs except maybe ARM are essentially dead in the general purpose computing, and the CISC is the one CISC is still around. Here you have some more recent architecture. I think there is not much to add, but you can go around. You see that, for instance, the decoder becomes wider to try to do more things at the same time. The retire unit is essentially the reorder buffer, so it's the same thing that we had before. This is the companion microarchitecture from AMD, again with these schedulers, which is a name for the reservation stations, and here the retire unit, which is again the reorder buffer. They are essentially equivalent. And this is the other image that we have just seen previously in the course about the microarchitecture, the ARM implementation by Apple of the Firestorm microarchitecture. And what we see here is one number that I think is interesting to read, which is what is the size of a reorder buffer these days. It's huge, right? What exactly it means and why this odd number, I have absolutely no idea. But there is one thing that I find interesting to read from this. 20 plus years ago, I was working in a company that was doing essentially embedded processors, or chips that contain processors embedded in the chip for the phone market. Now, of course, the phones 25 years ago or 22 years ago were very different from today. But I remember that there were discussions of the following sort. Intel is going to be completely out of any of these markets because they do these extremely complicated processors where they waste a huge amount of power because they are doing all this out of order and so on. Now, I have learned a few years ago to believe that people always want performance. People always want bigger storage. Just there is no limit to the interest by people for by the world of computer science for more capability. And I was very skeptical about this, right? And these people were saying, no, but absolutely, super scalar, forget it. Speculative, oh my God, absolutely not, because speculative means that you're doing operations that you throw away. Now, this is a perfect example of how these things always go wrong, right? The fact of assuming that you'll give up on some fantastic performance improvement is never going to happen. This is a macro architecture that has been invented by Apple for a number of certainly commercial reasons to get independent from Intel and getting more money from their laptops. But part of it is, and one of the data that we know of this microarchitecture is to be significantly more energy efficient from the Intel architecture. Now, is this not doing speculation? Absolutely not. In fact, you go back, I don't know the numbers for these retire units, but I know the number of this one. Here we have a reorder buffer with 128 entries a few years ago, and this is doing even much, much more. So the problem is not giving up on the great things that give you performance. The problem is implement them well. Make sure that the implementation is done in such a way that you are careful for energy. And this goes back to my introductory joke of the first criteria for optimization is speed, the second is speed, the third is speed. Energy is important. Energy is, of course, essential when we have these laptops that we want to operate for a few hours without recharging, and our telephone that has to operate at least until tonight when I will recharge it. But is not the primary optimization criteria. It's more a constraint. I will play every game that I can to get performance within some boundary of what I can consume. Thank you very much, and see you next week.